Okay, and with the recording going, I think it's time to welcome you all to the SAZERAC SIP, a meeting devoted to discussing and learning about metals and dust in the high-redshift universe. This that you are seeing right now is the webpage of the SIP, where you can find some of the information. And there is, of course, a Slack channel that we are going to use for asynchronous question and answer. And first of all, let me introduce myself. My name is Enrico Garaldi. I'm currently a postdoc at the Max Planck Institute for Astrophysics in Munich. And I'm one of the organizers of this SIP, together with Benedetta Ciardi, also at the Max Planck Institute for Astrophysics, and Valentina Dodorico at INAF in Italy. So yeah, this meeting wants to just bring together the community working on high-redshift metals and high-redshift dust. As you have seen, we are going to try to make this live on YouTube. Tomorrow, there seems to be some server-side issues today, so we're just going to record the meeting. Just a few very quick organization notes, and then we're going to start with the talks. The first one is that in the tradition of these SAZERAC SIPs, we are going to have the talks live on Zoom. And then the Q&A after the talk is going to be on Zoom for the time we have. And for any additional question that cannot be asked on Zoom because of time constraints, you can find on the Slack channel a thread for each talk. And so we ask you to write in the appropriate thread your questions so that the speaker can then go on Zoom and later on reply to the questions. There can be discussion below the thread. There will be some of us on the Slack. Just if you have any issue, you can message me or I will be, since I will be busy sharing this, you can message Andrea Saccardi or Aniket Bhagwat or Argyadeep Basu that are part of the log for this meeting. And of course, Benedetta and Valentina are also there. So one last couple of things for the speakers. If you have a video in your presentation, please, once you share or before sharing, click optimize for video streaming, which will just make the video visible on people on YouTube, but something a frame rate larger than 3 frames per second. Yeah, we ask you to stick as much as you can to the time, because we have breaks planned, and we don't want to we want to have some breaks, so we don't want to run too long. And the chair of each session, and this for now myself, is going to give you a 3 minutes warning. 3 minutes before the time. And with that said, I forgot to mention, you can find the schedule either on Slack or on the conference website here. And with that said, I would say that we can start with the first invited contribution from Kirsten. So we'll stop sharing. And so I'm Kirsten Kragberg-Knudsen, that will tell us about metals and dust in the early universe from an observational perspective. So I would say just take it away from here. I will give you a 3 minutes warning.
And I'm obviously muted as well. So thank you for introducing as well. And when I've spoken too long, just shout at me if I don't notice that you're trying to reach me. So, okay, well, I want to thank for being invited, for actually giving the first talk here. And it's the topic of metals and dust at high redshift, and particularly epoch reionization, is both a very broad and a very fairly focused topic as well. And so I'm going to try to go through some of the little bit sort of introduce slightly some of the basic parts of this. There's a lot of research going on, so I'm not going to by far not be able to do justice to everything that's happening, but this is also the point of some of the talks that come afterwards, is that there is actually going to be a lot of in-depth information coming, or in-depth presentation of results instead afterwards. So I hope that what I say will sort of lead into to some of the what comes afterwards. And I've taken the observational point of view, and I realized while I was preparing as well is that it's maybe a little bit biased towards the long wavelength and to the radio and submillimeter part. But I have to say that it's the whole electromagnetic spectrum that is extremely important for understanding the role that our understanding has for both like metals and dusts in those very early times. So let me just start with one of those very classical slides or images that has the history of the universe condensed into a very short duration. And of course, when we talk about the epoch of reionization, we're basically talking about the time that leads up to 1 billion years after the Big Bang. We're looking at redshift beyond redshift 6. And at the one end of the universe today, we're here, and it's about 13.8 billion years after the Big Bang. So from redshift 6 until today is actually a lot of time. But it is the first billion years play an immense role for what happens afterwards, and basically sets the stage for all galaxy evolution that happens afterwards. So from the Big Bang, we get basically a very limited periodic system that mostly is hydrogen and helium, a little bit of lithium, and that's where we start from. So when we talk about metals, and this confuses people in other topics, not astronomers, is that metallicity and metals is basically everything heavier than helium. And all of this is basically the products that come out of what happens in galaxies, namely what happens in the inside of the stars, where we have the nuclear synthesis. And that are the products that come out of it. And therefore, it's really important to understand what goes on at various types of galaxies and at various times as well. So it therefore is very important we get the first stars and the first galaxies, and we're gradually pushing out to actually finding the furthest away and most distant galaxies in order to actually reach to the earlier stages. So let's sort of start. Why do we all care about the metals and the dust during this time? And here's a very sketchy version of what, like a galaxy, trying to sort of just get an illustration overview of what's going on here. So in the inner parts, in the galaxies, which are by themselves not actually that big, there is all the gas, and from the gas we have the star formation. From the star formation we get the stars. They go through their life. We get stars evolve stars. We get supernovae, and we get other means of returning basically all the gas from the stars back into the interstellar medium as well. And getting any kind of, even the first part of the metal content in the interstellar medium is vital for actually getting a more efficient star formation process as well. And we also know that a lot of metals that basically get themselves locked into these little solid state particles that we know as dust grains. And the dust grains will lug in what there is in the gas phase, not all of it, just a smaller part of it. And in very, very rough numbers, we typically talk about a gas mass to dust mass ratio of about 100. So about 1% of this is locked into the solid state phase, but the dust is extremely important for regulating a lot of the processes. So in the inner parts, this is sort of, well, not fully in the inner parts, but a big part of what's happening in the galaxies is this. Of course, there's gas flowing in and there's gas flowing out. And this, of course, reaches to the circumgalactic medium and then further out to the intergalactic medium. From the massive young stars, we get a lot of ultraviolet light. And at the epoch of reionization, this ultraviolet light has to come from the stars or also from the AGNs, the early active galactic nuclei, and out into the intergalactic medium where we have the reionization process that takes place. And so what happens here is, of course, this linking between the somewhat smaller scales of what happens in the galaxies up to the cosmological scales. So as I said, so metals and dust, why do we care about this? This is basically the cosmic recycle place. It is where we actually have the chemical enrichment of what's happening. Without the metals and without the dust, we have a harder time having a regulation on the heating and cooling processes. And this is in particular important also for the UV radiation that we get from the young stars. So when we do the observational point of view, this is our means for actually understanding the star formation, understanding actually we have means of measuring the metallicity, and part of that I won't actually talk specifically about measurement of the metallicity, that will come in the talk after me, I think. But we have different ways of probing the metals, the content, the radiation fields. Finding the dust content is also an extremely big challenge of the observational site, but it is a very important input to a lot of the modeling as well. And we can get from looking at the gas, we can get things like the kinematics, excitation, and these kind of things. On the other hand, again, I just want to reemphasize the epoch of reionization basically constitutes the early stages of galaxy formation evolution. It's also the early stages of the supermassive black hole growth. And there's also this time where we get the onset of the enrichment of the circumgalactic medium and the intergalactic medium. And then, of course, one thing to remember is that the cosmic microwave background radiation has an effect on observations. So I'll touch a little bit more on that in a moment. But for us to really make progress and understand the theoretical side and the observational side, getting this really distant part of the universe, which for us is challenging, observationally challenging to observe just because everything is so far away, everything's a bit dimmer, everything is a little bit more blurred, galaxies are small, and just the sheer distance mean that everything is very difficult to resolve in the sky as well. So we need to find good measures for actually mapping between observations and actually understanding the physics and actually providing that meaningful input into the observations, to the theoretical modeling. Now, I just want to take one jump back to some of the just to highlight the immense development that's been over the past couple of decades. So it's been in the early 2000s that it really sort of got significantly going in observations beyond redshift 6. And here I have two different examples, but of course, it doesn't do justice to the immense efforts that have been happening afterwards. But the one at the top is one of the first ALMA emitters on redshift 6, which by Hu et al. And the bottom one is one of the Sloan Digital Sky Survey quasars at redshift 6.4. That one was also one of the first dust detections of those redshift and also molecular gas detections. And the reason why I picked these two as examples is that they represent two very different parts of the luminosity function of the type of galaxies we find outside of us. So it's like we look at galaxies today, we see there's a reasonable variety. We look at the early universe, there's enormous variety in the stages we're seeing. One of the more recent results was from Haigan et al. And Pakuchi et al. Actually showing so far, I think, the highest redshift candidate galaxies and pushing in beyond redshift 13. And so, of course, this is where we're sort of getting into what's the early parts. And we're very strongly here relying on this multi-wavelength analysis to find both looking for dropout galaxies, but also being able to actually get their redshift detections. But there are more of these coming and it's progressing. Maybe if we give this talk in 5 years from now, JWST will have given an enormous, increased our sample here. So if we look at, as I said before, there is a quite range of galaxies in the early universe. And if we look at, for example, the UV luminosity function, they're presented in various papers in the literature. I've taken one from Richard Bounds and some of his analysis. But again, there are many papers doing this. And one of the things that's important to notice is that there's an indication that the shape of the luminosity function or sort of the distribution changes with time as well, changes with redshift, which of course also gives rise to what is the relative contribution between sort of the fainter end and the brighter end as well. And that plays a big role in how we also understand what are the galaxies that are responsible for the reionization of the intergalactic medium. Having said that we have both sort of the lower luminosities and the higher luminosity ends, and these play different roles. Like the high luminosity end really represents the more massive systems, and therefore also the places where possibly that the evolution goes a bit faster. And of course, we know from slightly lower redshift in the local universe that we have the mass metallicity relation, and that metallicity tend to be higher in the more massive systems. Now, that of course is interesting because we need the metals, we need to have some degree of metallicity in order to have the dust production as well. And therefore, it's also interesting to see what are the different kind of dust detections we have in the early universe. And in fact, we have dust detections over basically the whole range of the luminosity function. So the arrows I put on here is not to give the exact UV luminosity these sources have, it's just sort of give an indication that two of the sources that we have here, which are in the lower part, is a quasar and a starburst galaxy. They represent the brighter end, while on the lower end, on the sub-L star part of the luminosity function, we're actually also having dust detections. And as it goes with many different parts of this kind of research, a lot of this starts with there is one detection, two detection, more detection, and then gradually more detection. And of course, in the coming years, we're going to see this in a much more systematic basis. And I hope I'm going to be able to show you some of the initial parts of this as well. Now, I want to just highlight a couple of different effects that one should think about when talking about looking for the interstellar medium and looking for metallicities and looking for dust, etc., in the early universe. And one of them is when we look at dusty galaxies, one of the effects we know is the negative K correction. I want to use this illustration, which is from a review from Hutch and Acuna from 2 years ago. It's a very nice figure that shows that if you take a spectral distribution for a particular situation and you sort of fix it with a fixed luminosity as well and gradually redshifted, then as we're going, things of course become dimmer as they go to a larger distance with redshift, but because the redshifting of the spectrum itself means that we're actually going gradually up the on the Rayleigh-Jean slope of the far infrared side of the far infrared SAD, also means that we're actually going towards the peak, and that means that around this sub-millimeter range, out to about redshift 6, 8, or 10, depending on the wavelength, we'll actually be able to see dust galaxies provided that they actually exist. And of course, we've already seen examples that these exist. That means that there is a good opportunity for looking for dusty galaxies. Again, this is where we're still trying, like one still has to understand if the properties remain the same. So here's a figure from, and this is mostly just used to, I want to sort of illustrate that we have dusty galaxies detected out to very high redshift, but also like the discussion about the relative contribution between obscured and unobscured star formation. And so this is from the 2 millimeter survey from Moore survey that was published recently, where the two different colors represent, based on observational results and modeling, sort of represent a little bit that as we go out to the very high redshift, we see that the unobscured star formation probably is a slightly larger fraction as well. But that doesn't mean that dusty galaxies are not important, and it's extremely important again for understanding the properties here. So as I said before, the cosmic microwave background radiation is also important for understanding, has an effect on how we do the observations. The temperature we know today is below 3 Kelvin, but it scales with 1 plus redshift. And so beyond redshift 6 actually means that the background radiation field is more than 20 Kelvin. And again, as we progressively go to even higher redshift, that of course means there's even higher temperature. That is an effect that plays a really big role. And there is a number of papers out on this, and one of the ones that has, I've taken a figure here from the Cunha et al. 2013, which has was nice. It shows the actual impact of having an SED and then having the ECMB effect included. It gives what one actually sort of should expect to be observing. So this plays a role as well. Another thing that to keep in mind, and this is an illustration from one of Susanne Madden's paper, is what the metallicity and how that affects our ability to actually trace the ISM. So if we look at just directly on the left-hand side, the solar luminosity, solar metallicity situation, what we typically see is that the molecular gas, the H2 gas, is very well traced typically by the so this is sort of just molecular clouds, and at the sort of somewhat outer surfaces or the outer edges of this is where we have the PDRs, and this is also where we actually then probably see a lot of the carbon plus and the neutral carbon and also the neutral oxygen as well. But if we look at a low metallicity situation, and this is both what we see in the local universe, but also what possibly is the situation we see the high redshift universe, is that the molecular gas is not necessarily traced very well by the CO. It's probably better traced by some of the other traces like neutral carbon or ionized carbon, or even also by oxygen as well. And so it means that we have to rethink a little bit about what are the most traditional traces that we have. Can we still use them if we want to study the low metallicity environment, which is particularly important for the fainter end of the luminosity function, but could even just be generally important when we look at the high redshift, at the epoch reionization galaxies. So this is another effect to sort of really keep in mind. But this is a Ben effect, mostly particular if we're looking for the, in the long wavelength, and we're looking at the gas. So metallicity determinations are very important. And so hopefully, again, this combination between having the optical and the infrared observations together with the far infrared helps us understand the relative ratios of this of the different lines. Now, tracing the far infrared, tracing the interstellar medium, which of course is again what affects the star formation, and from the star formation we get the stars, we get the chemical enrichment out of into the interstellar medium again. We have this recycle. What are some of the efficient ways of doing that? So fine structural lines in the far infrared actually has a lot of promise and provides a lot of this. And that, of course, is very important also because ALMA provides us with the tools to actually do these observations. So what we know from the local universe is that if we look at the star formation rates compared to the luminosity of some of these fine structural lines, is that there seems to be a reasonable correlation. And therefore, it's also been suggested that, for example, carbon plus, which is the one at the top, is a very good tracer of what happens and a good tracer for star formation in early universe galaxies, because going from 1.9 terahertz in rest frame wavelength, rest frame frequency means that it redshifts quite nicely into the millimeter bands and therefore is very easily observable from the ground. Some of the other lines like oxygen 1 and oxygen 3 are also somewhat easier to access also for the high redshift universe. And therefore understanding the relative contribution is important, but again, like for a long time, carbon plus was considered this is probably the one that's going to help answer all our questions. It turns out it's not quite as trivial as that, but again, it's a good starting point. So let's just sort of take as an example from, there's a large number of papers out that have actually, because the number of carbon plus detections has increased quite significantly over the past 10 years, basically, like since we got ALMA, but also NOEMA is contributing quite significantly to this. And so using the carbon plus for tracing this. So this is one of the many plots that are available in the literature. This is the one from Hardikan et al. 2020, and I sort of like the compilation of this, where we have sort of the higher star formation and still regular galaxies without a significant ADN contribution, and then we have the fainter end down here. There are many more spectra in the literature than what's in the background of this slide, so please don't feel forgotten. This is just a sample. It also turns out that if one were to plot up at the bright end, the few very strong starbursts and quasars, one would see that it sort of also has a reasonable agreement. But the fainter end is somewhat more difficult, and there seems to be many more, upper limits. There are many more non-detections as well. And again, I'd like to emphasize really important to get the non-detections published. So what to do about some of this? There is a number of, to really sort of get systematic observations going, it's very important to get these large programs. ALMA offers us, just like the other big observatories offer large programs. And I want to emphasize two here, which are really pushing into redshift 6 and beyond, which are the ALCS and Rebels. I have to say Alpine, which is on the list just above, also just touches between redshift 4 and redshift 6. But now ALCS and Rebels are the ones that are coming out with a number of publications very at the moment. And I'm sure that we'll hear more about these, in particular from Rebels, also during some of the other talks. So from the ALCS, the ALMA Lensing Cluster Survey, which is also 33 galaxy cluster fields, looking at redshift 6 sources, trying to actually, there's a couple of the actual detections, but there's a lot of non-detections. And so in one of the papers by Julie et al. Has been trying to look for using stacking, spectral line stacking, to try to put some upper limits. This is not quite trivial when doing this for galaxy clusters, because of course there's the whole magnification that has to be taken into account. But it basically sort of here on the right-hand side, this is one of the figures from that paper showing the upper limits with sort of different subsamples, and they would basically correspond to laying over here. And so there could be different reasons for why we're not actually seeing getting as many detections there as maybe was expected, and it could either be observational related to whether we're actually going deep enough, or like the depth should be okay, but it could also be like if the UV coverage is okay or not. There is a bunch of things to that, but there could also actually be very physical reasons to this, and this could be intrinsic to the properties of the galaxies. Some of the modeling that has come out over the past few years suggests that, for example, the metallicity could play a role in the predictions between the star formation rate and the line luminosity, the carbon plus line luminosity. So metallicity is probably not the only reason for this. There could be other reasons for that as well, but metallicity could play a role, and therefore it's very important we get a handle on on measurements of this. So these are actually just from plot models. There is a couple of papers on this in the literature. So taking again from the Haddocan et al. 2020 paper, I want to emphasize that while carbon plus is a really great line, and there's an enormous amount of line, there is a increasing number of lines being detected. The other one that's really important and it's very comparatively bright as well is the oxygen 3 line at 88 micrometer, 88 micrometer. And those two lines together, because they're some of the brightest ones, also the ones that are being used at the moment to try to sort of probe a bit about what are going on in the high-redshift galaxies. And so the plot here at the top from is sort of shows the ratio as one would expect it from local galaxies, both starburst galaxies and low metallicity dwarf galaxies. What we're finding generally for the very high redshift galaxies is that they tend to lay above both of these relations, that the oxygen 3 is actually relatively bright compared to the carbon plus, more than one would expect. This could, of course, have a number of different reasons. It could be that the UV radiation field is different. So the ionization parameter, we could have that the PDR, the covering fraction of this, so it's sort of the whole distribution of the matter and the clumping, etc. And the density of the gas could also be metallicity that has an effect on some of this. So like one can model this using different methods. There is not necessarily a unique answer to why this is. And part of this is, of course, that we have a hard time resolving the individual sources and finding their exact distribution, but it's also the fact that we're still limited in number of sources to really understand, are we seeing just like the few extreme examples, or are we actually seeing the general population here?
3 minutes.
Yes, okay, I'm going to speak faster. And so this ties in the necessity with the modeling as well. Okay, let me then just go to the next one here, which is that the dust temperature is another way of looking at. So instead of looking at the gas and looking at the metal lines, actually looking at the dust as well. And so I can sort of advertise that what Laurens and Enrico is going to talk about tomorrow as well relates to actually understanding the properties with the dust and looking at the temperature distribution. And one of the things that's really important here is that Rebels is actually contributing a large number of detections that we need in order to understand some of the connection between the high redshift universe and the low redshift universe. That was the short version of that. I'm just going to jump on to the next part. So another aspect, of course, not just looking at what happens in the galaxies and the inner part where we see the stars, but actually looking out in the further regions as well. And one of the big questions here is, of course, are we looking at still just extended disk, extended interstellar medium, or are we actually looking at the circumgalactic medium? So there's been a number of sort of gas halo detections. This has primarily been done with carbon plus observations. And what I'm showing here are a couple of different results, where one is stacked result looking at ALMA bright galaxies, seeing this extended carbon plus, but there is also indications from the quasars that there could actually be a little bit that the carbon plus is more extended. And this is somewhat related to also seeing at this slightly lower redshift between redshift 4 and 6. So that is a very big question. We don't have the answer to this. Is this the CGM or is this just extended ISM? But this is linking up to the next level of how do we transport how does the enrichment happen from the galaxies themselves and out into the CGM and further out into the intergalactic medium? And outflows and the AGN feedback is a very hot topic, not only at very high redshift, but throughout any redshift, basically. And the question is, can we detect this? How do we see this? And how do we measure the feedback? And this is not only to understand the regulation of star formation, because of this could have an impact on the star formation, but it's also understanding how do we get the transport of the gas, the outflows of this. And so while previously it's been suggested that, for example, in redshift 6, we could have quite significant outflows, as seeing in carbon plus, we're having this really bright, very broad, high velocity wings. More studies looking at different different redshift 6 quasars, by stacking have suggested maybe a detection, maybe not a detection. There are different results in the literature, and so this is not quite a settled topic. But for the redshift 6.4 quasar J1148, new data, NOEMA data came in more recently. It's been published showing that with this newer data does not show the need to actually have this high velocity extended component. So that in itself is very interesting. But the question is also, are we using the right approach for actually doing looking for the outflows? And one of the more recent papers by, and Justin, I'm really sorry, I forgot to get your reference on it. This is from Justin Spilker's paper, where looking at OH absorption and making a direct comparison to the carbon plus. This is for starburst galaxies, a redshift around 4 or 5. But of course, what we see there should be similar to what we see beyond redshift 6. And so the question is, how can we really look for the feedback, and how can we look for the outflow, and then what tells us how we get the transport of the metals out? Now, we do know that there are actually the enrichment in the circumgalactic medium and in the intergalactic medium. And so I want to show just another example before I finish. This is from absorption line studies, where finding oxygen 1 absorbers or just metal absorption lines in front of quasars. And this is a particular example where the ALMA observations that followed on this was actually able to get a carbon plus detection at the position or at the redshift that corresponds to an oxygen 1 absorption line. And so this will sort of be the next step in trying to understand the levels, like the chemical enrichment as well, further out in the going from the galaxies and further out. Okay, so I'm at the very end. I'm just going to put up very quickly that in early galaxies, what are some of the important challenges? One of the things are the timescales, because we need to have the stellar growth. So we need to have the production of the metals and increase the metallicity and actually the dust. One of the things we don't understand is the star formation history, or at least we don't have very good constraints on this. It's the star formation history. And the question is, what initial mass function should we use? And again, I emphasize that we have quite a variety of galactic environments in the environments in galaxies, and also quite a big mass range. If I go further down, the UV radiation field is very likely to impact a lot of what we see, in particular in the dust properties. And then also the fact that what we see in the very early galaxies, in how the density distribution is, how the turbulence, the effect of feedback and turbulence and so on, will probably have an enormous impact on the grain growth as well. So like the dust properties that we're seeing. And I'm just going to stop there. I'll leave out my summary and just saying, like, observationally, this is like a fantastic time to actually do our observations. There is like new big telescopes. They're providing an immense amount of data, and the results are just amazing. So I'll stop there.
Thank you very much for the very nice talk. So if there is any question, please just either raise your hand on Zoom or write the question on Slack, and I will read it out loud. Okay. See on Zoom. Yeah, we have a question on Slack already from Christian Finlator that says, when considering ratios of emission lines from different atoms, non-solar abundance ratios are a potential issue. For example, high O3 over C2 could represent alpha enhancement. Are there independent ways to constrain departures from solar abundance ratios?
That's a very excellent question. I think that I know this has been suggested, I think also in some of Halikat's modeling as well, where like that the CO to oxygen ratio could play a really major role in these ratios. I think maybe there are other people as well who would be very good at answering this question. Maybe we can have a little discussion on that on Slack.
Okay, for sure. It's there for that reason. More questions.
Like, I think if we were in the local universe, I'm sure that there would be many more ways of actually doing these observations and actually doing the observational constraints. But the problem is, in the high-redshift universe, we're very limited in the signal to noise. So just to continue in Christian's question while you were waiting for others.
Yeah. I don't see one, so I will ask you one in the meantime. And my question is about sizes of the galaxy that we are looking at high redshift. Mm-hmm. So that's I remember, some time ago there was this discussion whether we are reaching big globular cluster sizes or not. And so I was wondering if to connect back to metal and dust, if there is any way observationally we can use the constraints we have about metals to tell something about this issue?
It's a very good question, because if we can resolve it, we can get a better handle on sort of where the enrichment takes place. So there's a couple of, and I haven't shown this, we actually have some results on resolving lens galaxies, trying to get the individual, sort of somewhat individual clumps or components of this. And at least in one of the galaxies, we have a redshift 7, we don't see enormous variations between each individual part of this. We see it within a factor 2, maybe some variation, but not enormous variation. This is based on carbon plus and the oxygen 3. But of course, that is in the same galaxy system. So the question is, if we now had things that are moving in together from different places, maybe the enrichment will look, their chemical status will look different. I also think if we move towards really redshift 6 and maybe are able to look at the star forming regions versus having sort of the overall galaxy, maybe we can see that it differs a bit as well. So.
Okay.
But again, we need to be able to zoom in on this like kiloparsec or sub-kiloparsec scale, which is very tricky.
Of course. Yeah, of course. I was thinking more like, these cluster lenses.
Yeah. Well, the cluster lenses are probably the best way to go for this.
I would say one last question from Slack. Il Sang-Yon asks, can the current observation give us any insight on POP3 stars?
Okay, sorry, can you repeat it again?
Can the current observation give us any insight on POP3 stars?
Oof. I think that's a very difficult question. So unless we can link the POP3 stars to the enrichment and maybe the metallicity, then we can probably, yeah. No, I think with the current observations, at least we have on the far infrared side, it will be very difficult to link directly into this, unless we have models that tells us that POP3 stars will give us an enhanced oxygen abundance. Maybe this is about the only thing that we can get. So, but otherwise, no, it's difficult. I think we need to be more at this up in the optical near infrared part of the spectrum. So.
Okay, thank you very much. I don't see any other questions for now. But I'm sure there will be. So if you can have a look at Slack later on.
I will look at Slack. Thank you.
So thanks again. And I asked the next speaker, Amiri, to share the screen.
Sure. Can you hear me?
Yes, perfectly.
And do you have my slide? Okay.
We do have your slide.
Perfect.
So please, again,
yes.
3 minutes warning. Take it away.
Thank you very much. It will be a nice pleasure to be here, and a special thanks to organizer for shaping this very interesting program. Today, I want to address about part of my PhD thesis for measuring metallicity with a new multiple component photoionization model. To investigate about how galaxies evolve, there are different key subjects that we can study. For example, the global properties such as the coevolution between the central black hole and the galaxy, the stellar evolution, nuclear activity, morphology, redshift, and so on. And all of these items can directly affect the evolution of the metallicity in the both large scale structure and the small scale structure. To studying how metallicity is evolving in each classification can give us the highest information on the galaxy evolution. To estimate the metallicity mainly, to determine the metallicity mainly, there are two approaches. One approach is based on the sample of the observations. We call it the empirical methods, that we can directly use the information inferred from the emission lines in the spectra. And through all of the sub-branches, one of the more precise method is using the auroral line or direct method, or TE, that they are very faint optical emission lines, but they are very sensitive to temperature. And if you can observe these emission lines, you can estimate metallicity with high precision. And for example, the important emission lines for the auroral lines, we can call the O3 4363, O2 7330, and so on. But the problem is that although it is very good method to estimate the metallicity, but they are very, very faint. Regarding to the limitations on the observations, people have been tried to compute a couple of the models based on the photoionization models to provide the emission lines similar to the observed one, estimate the metallicity. But through the last 2 decades, people have been trying to use the single cloud model to
Okay, let's see if we can get minutes back. Okay, I see other people moving, so it's not only me, which is good, because I was worried. Okay, for a second. Okay, let's give it another 30 seconds. Otherwise, I would ask the next speaker to just be ready in case it doesn't come back. Okay, I would say then let's move on to Yuichi, and then we'll listen to the talk once he manages to connect back. Is that fine with you, Yuichi? Okay.
Yeah.
Then, yeah, please. Okay, so next up, surprisingly, is Yuichi telling us about metal enrichment in redshift 6-7 galaxies. Please.
Yeah, okay, so can you hear me?
Yeah.
Okay, good. So hello everyone, I am Yuichi Harikane from University of Tokyo. So first of all, I thank organizers for organizing this very nice conference. So today I will talk about metal enrichment in redshift 6 to 7 luminous galaxies. Okay, so the metallicity in high-redshift universe is important because it's related to many important topics in galaxy formation. So for example, the star formation history, gas inflow, and outflow. And here I show the mass metallicity relation. So y-axis is the gas phase metallicity, and the x-axis is the stellar mass. Okay, and mass metallicity relation is constrained up to redshift 3 up to 3. And it's important to extend this kind of study to redshift beyond 5 to understand the chemical enrichment in early universe. However, the measurement of the gas phase metallicity at redshift beyond 5 is difficult. So this figure shows the SED of redshift 7 galaxy. So the use rest frame optical emission lines such as O3507 and H-alpha that are very useful to estimate the gas phase metallicities are redshifted to the infrared wavelengths, okay, where the ground-based telescope cannot access. And of course, JWST will detect these emission lines, but before JWST, actually we can roughly estimate the metallicities in these high redshift galaxies. Which is, I think, good practice for JWST. Okay, so in our study, we use 31 galaxy spectrum at redshift 6 to constrain the metallicity of these redshift 6 galaxies. These galaxies are very bright, minus 23 magnitude in UV, so we can detect absorption lines. Okay, and 2 of them are observed deeply with VLT X shooter. So here I show the spectra of VLT X shooter. So we can detect lime alpha and several absorption lines here. Then we stack the spectra of 31 galaxy at redshift 6. So here I show the composite spectrum. So we can clearly detect these absorption lines, metal absorption lines such as silicate 2, carbon 2, and we can also identify these stellar absorption features. So these metal absorption lines are useful to estimate metallicities in these redshift 6 galaxies. But before going to metallicity, actually we found that these absorption lines are very deep. So here I compare our absorption line spectrum with redshift 4 less luminous galaxies. So red line shows a redshift 4 spectrum, composite spectrum with a magnitude of minus 21. Okay. So for example, if we see this carbon 2 absorption lines, our redshift 6 bright galaxies shows deeper absorption lines than that of the redshift 4 less luminous galaxies. So this indicates that our galaxies have large covering fractions and low escape fraction of ionizing photons. Okay, so in order to quantitatively discuss this, we make the composite spectrum of the low ionization absorption lines, such as silicate-2 and carbon-2. So this is a composite spectrum of the low ionization absorption lines, and then we measure the maximum absorption depth. Okay, and then if the gas is optically thick, then this maximum absorption depth corresponds to the governing fraction of the low ionization gas. So this figure shows the governing fraction of the low ionization gas measured as a function of the UV magnitude. Okay, so red point shows our result at redshift 6, and the black point shows the less luminous galaxy results. So we found that the governing fraction is higher in brighter galaxies. Okay, and if the governing fraction of the neutral gas or low ionization gas is high, then it indicates that ionizing photons escape fraction is low. Okay, so our result indicates that our bright galaxies have higher covering fraction and lower escape fraction. So in other words, the cosmic reionization is mainly contributed by faint galaxies, which has a high escape fraction and low covering fraction. Okay, then let's go back to the metal things. So we detect several metal absorption lines, metal ISM absorption lines, and stellar absorption lines. So these absorption lines are useful to estimate the gas phase and stellar metallicities. So we estimate the gas phase and stellar metallicities. So regarding the gas phase metallicities, we measure the equivalent width of these metal absorption lines. And then by using the good correlation between the equivalent width and gas phase metallicities calibrated by lower redshift galaxies, we estimate the gas phase metallicity. So here I plot the calibration at redshift from 0 to 3. So regarding the stellar metallicity, we use these stellar absorption features and fit these absorption features with the bypass stellar population synthesis models by changing the stellar metallicities. And then we find the best fit stellar metallicity. Okay, these two panels show the result. So left panel shows the gas phase metallicity and right panel shows the stellar metallicities. So both of the metallicities are plotted as a function of the stellar mass. Okay, red point shows our result. So regarding the gas phase metallicity, we found that gas phase metallicity is relatively high, about 1 solar at redshift 6. Okay, you can also find orange data points. So orange data points are redshift 5 galaxies, and some of the redshift 5 galaxies also shows relatively high gas phase metallicities. Okay, regarding the stellar metallicities, in the right panel, we found that stellar metallicity is about 0.4 solar. So this is a subsolar metallicity. So we found that gas phase metallicity and stellar metallicities are different, but actually this is because these two metallicities are tracing different elements. Okay, so regarding the gas phase metallicity is defined by the oxygen abundance. On the other hand, regarding the stellar metallicity, the stellar absorption features are mainly made by iron. Okay, so this different gas phase and stellar metallicity indicates a supersolar oxygen over iron abundance ratio. Okay, about 2 times higher than solar abundance ratio. And actually, this supersolar oxygen over iron abundance ratio is consistent with the metal enrichment by the core crop supernova rather than the type 1a supernova yield. Also, we conducted calculations by using the chemical evolution model. Here we assume constant star formation history and also assuming the yield, metal yield from core crop supernova and type 1a supernova. So this figure shows the calculation result. So y-axis is the metallicity and the x-axis is the time after the initial star formation. Okay, and blue and red lines show the metallicity for the oxygen and iron, metal abundance for the oxygen and iron, and this dashed line shows observations for our redshift 6 galaxies. Okay, so we found that about 500 mega-year is needed to explain the observed metallicity. So and this 500 mega-year corresponds to the about redshift 10. So our calculation indicates that these redshift 6 galaxies, which is relatively metal enriched, should start their initial star formation and chemical enrichment from redshift 10. And actually, this very high redshift star formation is also consistent with a recent report from the major stellar population in very high redshift galaxies. Okay, then we found that our high redshift galaxies at redshift 6 shows relatively high metallicities, about 1 solar. So on the other hand, at redshift 8, around 8, then there are another measurement of the gas phase metallicity by using the ALMA 0388 micron line. So this study found that relatively subsolar gas phase metallicities. However, both of these measurements have systematic uncertainties, such as relative abundance, ionization parameter, electron density, and electron temperature. And of course, JWST will provide metallicity measurement at redshift beyond 6, but given these systematic uncertainties, we need robust measurement by the direct temperature method to overcome these systematic uncertainties. Okay. And in our JWST GO program, we think that we can obtain the metallicity measurement by the direct temperature method. Okay, so in our program, we will target 3 galaxies at redshift 6 to 7. Okay, the key point of this program is that our targets are already detected by ALMA 0388 micron line. Okay, and in our program, we will conduct non-spec spectroscopy targeting rest frame optical emission lines such as 03507, H-alpha, and O2. And actually, the ratio of the 03507 to 0388 micron depends on the electron temperature. This is because both these two emission lines come from the different transitions of the doubly ionized oxygen. Okay, so this is useful to estimate the electron temperature, but actually this ratio also depends on the electron density because both of these emission lines have different critical densities. So in order to break this degeneracy, we also observe O2 doublet to measure the electron density. So this figure shows a model calculation. So by using the O3 and O2 emission lines from JWST and another O3 emission line from ALMA, we think that we can simultaneously determine the electron temperature and density for redshift 6 to 7 galaxies. Then we can measure the oxygen metallicities by the direct temperature method. And in our program, we will also conduct NACAM photometric observations, so we can robustly constrain the stellar mass. Then we can place these redshift 6 to 7 galaxies in the mass metallicity plot. Okay, so this figure shows the mass metallicity relations, and we can discuss whether our redshift 6 to 7 galaxies have metallicities comparable to the redshift 3 galaxy or lower metallicities than redshift 3 galaxies.
2 minutes.
Okay, thanks. Okay, of course, and in addition, we think that ALMA 52 microemission line observations is very powerful to measure the electron temperature and density. So, for example, in the left panel, I plot the 0352 emission line to the 03507 emission line ratio as a function of the electron temperature. So actually, this ratio depends on the electron temperature, but does not strongly depend on the electron density. So this is very useful to estimate the electron temperature. Or similarly, the ratio of the 52 micron to 88 micron is sensitive to the electron density, but does not strongly depend on the electron temperature. So this is very useful to the electron density. And in particular, this observation is very powerful to determine the density in the O3 emitting regions, which is different from the O2 emitting regions probed by JWST. So this ALMA observation is very complementary to the JWST observation. Okay, so then this is a summary of my talk. So we present a spectrum of 31 luminous galaxies at redshift 6. So we clearly detect absorption lines, and these absorption line spectra indicate that gas phase metallicity is about 1 solar, and the stellar metallicity is about 0.4 solar. And this gas phase and stellar metallicity indicates that supersolar oxygen over aero abundance ratio, which is consistent with core crop supernova metal enrichment. We also found a very low escape fraction in luminous galaxies at redshift 6. Then we discussed JWST thing, and we think that JWST will provide metallicities by direct temperature method at redshift beyond 6, and also ALMA 0352 microemission observation is very powerful. Okay, so that's it, and I'm happy to have questions. Thank you.
Thank you very much, Yuichi. Okay, let me see. Is there any question? Please raise your hand or write it on Slack. Yeah, there is already one on Slack, so we'll go on with that. From Ashwin Vijayan that asked, writes, very nice talk. In case of the stellar metallicity measurement, I was wondering, since iron is expected to be highly depleted into dust, how much of an effect does that have in constraining the value?
So the question is about dust depletion, right?
Since iron is expected to be highly depleted into dust, how much of an effect does that have into constraining the value of the stellar metallicity, I think?
I see. Yeah, it's very good point. And actually, in our current calculation, we don't consider any dust depletion. So, however, our ALMA observation shows that the dust emission is relatively low compared to other high-redshift galaxies. So I think the dust depletion may not be significant, but we need has a detail, has a discussion, I think. Yeah. So that's an important point. Yeah, thanks.
Thank you. And then we have a question here on Zoom from Annalisa De Chia.
Hi, Yuichi. Thank you very much for the talk. It was really impressive to see this composite spectrum at redshift 6. I was really surprised to see such a high metallicity for the gas, like solar metallicity for the gas in this composite spectrum. And I saw that you derived it from a relation between, like some empirical relation between an equivalent width and then the metallicity. So I was wondering how solid is this method, like what are the limitations of this method?
Yeah.
What is it?
I see. Yeah, thanks. Yeah, that's very good point. Yeah. And actually, this is here we use metal absorption lines. So we are tracing carbon and silicon. So actually, if the relative abundance ratio will change, then the metallicity estimate will also change. And also, there is another uncertainty, for example, the ionization parameters, which affect these these absorption line depths and also the relative abundance. So yeah, there are actually many uncertainties. So and I think that we can definitely determine the oxygen abundance of these high-redshift galaxies by JWST. But actually, one point I want to have a comment here is that actually recent ALMA observation also show relatively high gas absorption. So here I show the ratio of the O3 to star formation rate. So here this green line is about 1 solar, and ALMA observation shows very high O3 to star formation rate. And so actually the gas phase metallicity about 1 solar is consistent with this ALMA observation. But yeah, I agree that we need JWST observation to conclude this discussion.
Thank you.
Yeah, thank you.
There are many more questions on Slack, so I will just pick one and then I ask you when you have time to just check them out. So just going in order, Il Sang-Yon asked, can you tell if the dust to metal ratio of the higher redshift galaxies is different from the one for local galaxies?
I see. Yeah, it's a good point. Actually, we don't have any estimate of the gas dust to metal ratio, but I think we don't have. Sorry. But it's a good point. Yeah, we need to think about that. Thanks.
Okay, thanks again, Yuichi. Again, there are more questions on Slack. And I would say, let's give it another try with Amir Nezam. Are you here? I see you connected.
Yes, and sorry for the interruption. Yes.
I'm sure it wasn't on purpose.
Down. So to continue just about my last slide, the slide 2. And so although the single cloud, mainly, for example, the local optical emission cloud LOC models is a single model to predict the best simulated emission lines versus the observations, they cannot take into account for the both high and low ionization lines simultaneously. So regarding to the single cloud, we cannot never provide both these ionization lines together or simultaneously together. So if we look at a real galaxy, we can see that a real galaxy is not a single unified object. So for example, when we are observing the spectrum of a galaxy, the emission lines are propagating from the different part of the galaxy, and at the end we have integrated flux for each emission line from the different places. For example, if we consider these star forming galaxies, we can see it includes a huge number of the different H2 regions with the different physical properties. And so in this case, it seems that for a more realistic model, instead of using the single cloud, we should consider the using of the multiple cloud. So for reconciliation between for reconciliation of the estimation of the metallicity from the observations and the simulations, it seems a more realistic model would be to the use of the multiple clouds. So first of all, for having a simulation on the H2 regions and generate the H2 region emission lines, to do simulations, we are using a photoionization modeling code with the name of the Cloudy. Cloudy is an open source plasma simulated course. And with the Cloudy, we can generate the spectrum of the emission lines, and mainly in this work for the H2 regions and the star-forming galaxies. The goal of Cloudy is to simulate conditions of non-equilibrium gas to reproduce or provide the emission lines, the level of the ionizations, the element of the ionization, the level of the populations, and the thermal states. The good point in the Cloudy is that the Cloudy needs a minimum number of the input. For example, ionization parameter, gas phase metallicity, number density of the hydrogen. And with using a stellar population synthesis library, we can have the continuum and we can do the simulations. And in the simulations, we are considering the ionization bounded case with the constant pressure. So in this case, we can have thousands of the models with the different properties in the ionization parameter, number density of the hydrogen, and the metallicity. From another point, we are using we need the observational sample. To use the observational sample, we are considering a stack sample of the galaxies from the Curti et al. 2017. They have used the full sample of the SCS SDR7 with approximately 1 million galaxies in the redshift 0.02 to 0.25. And we are considering just the star-forming galaxy based on the BPT diagnostic diagram without any contribution from the agents. At the end, they have 62 stack galaxies from these analyses. So we are using these 62 stack galaxies, and we could detect more than 40 emission lines. And the good point is that we could detect the auroral lines. The auroral lines, as I mentioned in the second slide before the interruptions, they are very sensitive. Although they are very faint as emission lines, they are very sensitive to the temperature. And if we can observe and detect the auroral lines, we can estimate the metallicity in a very good order. So here, I am showing a few interesting auroral emission lines, for example, O2 7319 and 7330. And here, for example, O3 4363 auroral line. And if you compare it with the other emission lines, you can see how they are faint. So from one point, we have a couple of the emission lines from the simulated H2 regions, and from another point, we have the observed emission lines based on the stack galaxy from Curti et al. 2017. To find which combination of the photoionization models can reproduce all observed emission lines from the observed sample from Curti et al. 2017, we consider a linear combination of the photoionization models. We consider a grid of model which varies in ionization parameter and number density of the hydrogen in a given continuum shape and metallicity of gas. And the best model is a combination of the weighted combination of each luminosity of the grid. The idea underlying this approach is that if a model can reproduce all observed emission line, this model includes the occupied volume at the right temperature. And if you have the right temperature, you can estimate the abundancy and metallicity in a good order. For example, for one of our stack galaxies, we can see that how chi-square varies as a function of the metallicity of each grid. And we can see that we have the minimum chi-square at the right value of the metallicity of the observed metallicity, and the observed metallicity is here for the blue vertical line. And at the minimum, at the right point, we have the minimum estimation for the metallicity regarded to the observed one. So previously, I just told that in the single cloud models, we cannot provide all of the low ionization and high ionization emission lines simultaneously. With considering the best model, which comes up from using the multiple clouds, we can see here that we can provide all low ionization and high ionization emission lines simultaneously. And mainly here we can see that the different emission lines in the different ionization state means that they are in the different temperature for the best model as a function of the observed one based on the multiple clouds. For example, O3 5007, O1 6300, O2 emission lines for the 3728, and S2 for the 6730. Also, based using of the multiple cloud, the best models, if we compare the oxygen 2 temperature versus the oxygen 3 temperatures, we can see that based on the aura lines, we can see that there is actually a simply increasing relations for the O2 versus the O3 for the best models. So we are saying that existence of the aura line is very important to estimate the metallicity. But if we don't use the aura lines, what happened for the estimation of the metallicity regarded to the observations? You can consider that all of the procedure, which I told you in the previous slides, but if we repeat all of this procedure without considering the aura lines, we can see that if we do not consider aura lines for finding the best models based on the multiple cloud photoionization model, which we have discussed, the deviations between the observed metallicity and the model metallicity without considering the aura lines makes more deviation on the estimation of the metallicity. So existence of the aura line and using them for estimation of the metallicity for the multiple cloud photoionization model is crucial. So we want to just check some calibration relation based on the strong emission lines. The gray stars are related to the best models which have been selected from the multiple cloud approach, and if we just do a normal fitting, my fitting to the gray stars are in the blue, and compare it with the other star and calibration line, we can see that we have a good agreement with the others, and we can reproduce it again all of the relations.
3 minutes.
Yes. So actually, if we consider our relation, for example, the anti-correlation between the ionization parameter and the metallicity based on the different reasons, we can see that all of our provided best models based on this situation has the anti-correlation with the ionization parameter means that when you have the higher metallicity, your ionization parameter should be decreased. And so exactly we can see here this kind of the relation. Actually, if we consider the ionization state with the other demonstrator of the metallicity, we can see this good agreement. At the end, if we consider some kind of the abundance diagram for the most important item, the N over O as a function of the metallicity, this plot or this relations has a dual behavior, a plateau or a constant relation for the low part of the metallicity, and it is based on the primarily production of the nitrogen. And whenever you are going to the high metallicity part, you can see the steadily increasing relation or trend that is related to the secondary production of delayed nitrogen by intermediate mass of the stars and some other channels that makes the steadily increasing trend for the high metallicity. So if you consider this kind of interpretations for N over O as a function of the metallicity, gas phase metallicity, we can see that the best model which provided based on these aspects, all of the low part have more or less the constant value, but in the higher part, you can see this kind of the trend, increasing trend. Although if you consider that other, for example, S over O abundancy as a function of the metallicity, we cannot see any special variations for this kind of the abundance. At the end, sum up with this fact that with using a multiple cloud approach, you can provide all of the observed emission lines through the different ionization states from the low to high, and other physical interpretations for the strong calibration, ionizations, anti-correlation with the metallicity, and N over abundancy versus metallicity can be positively provided with this method. Thank you.
Thank you very much. So I see there are already questions on Slack, so we'll start from there, but everyone should feel free to just raise their hand. So Il Sang-yeon writes, sorry if you already talked about this, but can you tell a bit more on how you sample multiple clouds, in particular in which parameter space?
So in the point, okay. So in this case, you can see that from the one point, we have all of the observed emission lines that you can see in the blue and the red point, the red color, and the red color are the aurora lines. And from another aspect from in the computation, we consider all of these observed emission lines as same as the observations. And we consider a linear combination of the photoionization models, which varies. Actually, we consider a grid which varies in the ionization parameter and number density of the hydrogen, with considering all of these emission lines completely same as the observations and the computation. And we use a linear combination of the photoionization models. So at the end, the best models means that they are the combination of the weights. For example, you should check that, for example, you can give a specific emission lines from the observations, and for this specific emission lines, you can find what is the best weights from all of the models that you have from the thousands of the different H2 regions. And if you consider this kind of the minimization for all of the observations depends on their weights, at the end, it means that you are considering you are considering the best models from the combination of the weights in this case. So your question can be answered in this case that you should consider all of the emission lines, luminosity of all of the emission lines in your observed sample, and related to this kind of emission lines, you can select all of the emission lines from the other models as a function as the best model.
Thank you. Another question from Slack from Mitchell Rewalski that writes, hi, Amir Nizam, wonderful presentation. Could you describe how your multi-cloud model weights are normalized, for example, to a Balmer line luminosity? And are the cloudy models constant density or constant pressure or neither?
Okay, very good question. In this case, we are considering a constant pressure, and when you are considering constant pressure, it means that you are permitting the systems that the density can vary from the low to high, and in this case, you have both low ionization states and the high ionization states simultaneously, and you can estimate everything very well. It is for the first part. For your second, your second question, actually, the first question, I should address about your question in details in the slide if there is no problem, because it has a lot of the details. So I think it would be much better if we address it in the slide for your first question.
Yeah, that would be great also because there is another question, and I'm sorry, Emma, we don't have time right now, but please write on Slack or maybe just stay online. Sure. There is a break in 15 minutes, so you can probably discuss during the break. So thanks a lot. I ask you just exactly to unshare. So the next speaker, Doug Renehan, can share.
Sure, thanks. Just give me a second.
Yeah.
Okay, don't look at my future slides. That's a spoiler alert. I gotta press play. Okay, great.
Okay, please.
Yeah, so thanks everyone. So already some very interesting talks so far. So I'm Doug Renehan from I guess I'll be from the University of Edinburgh in June for the summer, and then I'm starting as a Flatiron Research Fellow at the Flatiron Institute in New York in September. And I'm here today at this conference to talk about kind of a technical talk on simulations, but I'm going to keep it very simple because I know this is a very observationally focused conference, but I want to talk about why mixing matters for metals in the early universe in particular, and why I think a lot of cosmological simulations in particular need to be looked at more closely, whether or not they're accurate in what metal distributions they predict in this time range from about redshift, 8 to 4. So I'm going to start with a very broad statement. And I could probably end the talk after this if I didn't have to explain the caveats to every one of these individual words. But all hydrodynamical simulations require subgrid models for turbulence. Okay, and this is a true statement, but I'll go through some of the reasons maybe why this might not be true in all cases. But basically, if you're looking at the results from a cosmological simulation and you want to interpret those results, if they don't have a subgrid model for the turbulent mixing of metals, you can't guarantee that you're actually getting an accurate representation of the metallicity field in general. Okay, so so now I'll kind of go into the main talk, and I just want to talk about, in the early universe, and we've already seen this already in some of the talks, there are active galactic nuclei, and there's a lot of star formation happening, and both of these processes should inject a lot of energy into the medium. And really, it's a different picture than at redshift 0. At redshift 0, there's already kind of a circumgalactic medium that exists, but in the early universe, this is really the creation of the circumgalactic medium, and we're enriching something like the intergalactic medium. But both of these processes are very important, and as they eject metals into the medium and energy, they're mixing it all around on some time scale, and that's setting the enrichment of the region. Right. So I wanted to show an example of this happening on a very short time scale from a simulation that I'm working on of a protocluster core in the early universe. So this is a temperature projection of a zoom-in cosmological simulation of a protocluster core from redshift 7 to redshift 4. And I'm showing the temperature, but you can see there's a lot of evolution happening within this, less than a gigayear time scale. All of the AGN are activating, the stellar feedback is blowing out a lot of winds, and we're having enrichment happening. There will be a lot of metals in this outflowing gas. And this is also driving turbulence in that medium, which needs to be simulated accurately in order to know the metal distribution and the metal enrichment history of that new circumgalactic and intergalactic medium. Okay, so I just want to get into the problem. So I've already said turbulence mixes metals. I think everyone knows that. But what's really wrong with the simulations in particular? And the problem is that if you imagine, turbulence is a cascade of eddies. There's many eddies on different sizes that are happening in the flow. And if you slap down a grid or particles, it doesn't matter if it's grid or particles, the ideas are the same. If you put a grid over that and try to simulate it, you're going to have some of the eddies, which are represented by these ellipses, on a certain scale, which are resolved. There's enough grid cells to represent that rotating structure. But there are eddies below the grid scale, below the resolution scale, which you're not capturing properly. And those are actually contributing, or should contribute, to some level of mixing between the grid scales, between the grid cells themselves, okay? And this is true regardless of the hydrodynamical method, as I've said many times. But in this talk, I'm mostly talking about particle-based methods, okay? So we need some kind of model for how turbulence is occurring on the subgrid scale in order to actually capture how the metals should be flowing through the gas in reality. Okay, and the solution to this is to introduce some kind of additional diffusive process. I don't have time to say why this is true, but you can trust me for now or read my paper. But I'm showing one equation here. This is the diffusion equation, and this is a reasonable approximation to subgrid turbulence, okay? So we're now going to diffuse metals from grid cell to grid cell only on the grid scale size, okay? So we're diffusing metals between grid scales now. And there's some coefficient which controls the strength of this, which I don't have a lot of time to go into, but my paper explains how you can choose this. But my overall conclusion, I'm just going to say it now, is that it doesn't matter really what the strength is. Including this in the first place makes such a huge difference that it has to be done as a first step in all simulations. And there's not many simulators who actually include this in their models. So in the next tests, I'm just going to show you how we can calibrate these results, because a lot of people will argue that you can't calibrate them. I'll show that we can, and I'll show why it's actually required and what its impact is on the high redshift universe from cosmological simulations, okay? So when you're looking at the labels in the next plots, anytime you see colored lines these are just mixing models. Okay, these are simulations with some kind of metal mixing model. Any of the black curves have no metal mixing model. We don't have to go into the details of these, but just know that colored lines are mixing, black lines are no mixing. Okay, and I do tests at different resolutions. And to give you an idea of what some of the tests will be, this isn't actually my test, but this is a turbulence simulation from Christoph Federath. It's higher resolution than I was able to do, but I just want to show you like one of the tests where you can actually calibrate it is just in driven turbulence. So this is driven turbulence. It's just it starts as a uniform density gas box, and you just mix the gas over and over again to simulate what might be happening in like a patch of the circumgalactic medium, interstellar medium, or intergalactic medium, okay? So this is one of the first tests that I did in order to test these metal mixing models to show that they're actually required. So my tests involve driven turbulence. So, you start with a box of gas, you mix it for several mixing timescales. I injected metals into the densest regions and I mixed it again. And then what I want to do over several resolutions is just degrade all of those different resolutions up to the highest possible to the lowest resolution. So kind of averaging in cells into smaller, bigger and bigger cells, and then measure the metallicity distribution on the largest scale. Because no matter what the resolution is, they should all agree with the lowest resolution. If you filter it or smooth it down to that resolution, they should all be predicting the large scale metal distribution. The same, it's the small scale that should change. So the problem is that they don't. So here's a histogram of that smooth metal fraction, okay, from these driven turbulence simulations. And the black curves are showing the different resolutions I ran of driven turbulence, okay? And you can see that the black curves are converging towards some delta-like function, but they don't agree on the large scales, okay? So a low resolution simulation of 64 cube driven turbulence does not predict the same large scale metal distribution as 768 cubed. But what you can do is introduce a metal mixing model, these colored curves, and this will force mixing to happen that was not possible at that resolution. So you can get a metal distribution that's at a much higher resolution than you're able, because all of these colored curves are run at 64 cubed, but you could reproduce the same metal distribution that's happening at 768 cubed. And this is further encapsulated in this other plot I've included here, which is just the width of the distribution for no mixing models in black, and all of my mixing models at 64 cubed resolution. Okay, so this is the width of that distribution as a function of resolution. And you can see that at a low resolution, you can reproduce the same metal distribution as if you were at 256 cubed, right? And it doesn't converge until 768 cubed, which is a huge resolution that we can't obtain right now for a single galaxy. Let's say it's more like 64 cubed at our best resolution. So what impact does this have on, what we're actually measuring from a cosmological simulation so that we can test our observations or compare models? So I'm showing two slices here. These are two metal distributions from the warm hot intergalactic medium. So this is just the IGM and the CGM in a cosmological simulation at high redshift, from redshift 6 to redshift 4. So the black curve again, yeah, thanks. So the black curve is showing no metal mixing at all. And all of the colored curves are showing any of these metal mixing models that I include. And you can see that the differences in the metal distributions are drastic at high redshift, right? In this period of about a gigayear or so. If you include any mixing model, you're going to get tighter metal distributions. They predict higher metallicities than you're able to in other simulations. So, if you have something like Eagle-based simulations or an Illustris-based simulation, which does not include these models, your metal distributions are not tight enough. Because I've shown previously in the last plot and the last slide, sorry, that you can actually calibrate this and show that it improves the results. So there's a lot of work to be done, I think, and it's very important to consider this when you're interpreting models. So you can go ask the Eagle and Illustris team why they don't include this in their simulation and tell them to talk to me, I guess. Right, so that's actually all I have for you right now. I'll just leave you with these three things. So if you remember anything, it should be point one. It's that all of these simulations require these models. But I really want you to remember too that it is possible to calibrate them, and that the metallicity evolution in the early universe, in our models at least, or cosmological simulations, is highly sensitive to including or not including these models. So thank you.
Thanks a lot for the very nice talk. Okay, I see a question on Slack, so I'm going to go on with that. Juan Quinn Chen asks why fire looks very different from the others in the convergence plot.
Yeah, so I feel bad because I only included fire here. There are others that don't look as good. It's not that fire is necessarily bad. I mean, it is doing what it should. They just use a very low mixing strength. And I didn't want to get into the details of that because it would have taken a while, but all of these models do kind of change. They kind of converge when you like increase the mixing strength to the same result. You know, like there's a cluster of points here, fire's way up here. They're actually using just a very, very low calibration because they calibrated to dwarf galaxy stellar metallicities at low redshift. So they calibrated to something that depended on their subgrid astrophysical models, whereas I'm calibrating just to driven pure hydrodynamical turbulence. And I'm finding that you need a higher calibration to get a better result. Eventually, all of these will converge to the same result. So for example, at redshift 0, if I showed you this plot, all of the colored curves would predict the same distribution because there's been enough real hydrodynamical mixing to erase any effects of the subgrid scale. It's really in the times when you're just collapsing or just forming the halo. That's when the speed matters the most because it hasn't reached an equilibrium state.
Okay, thanks a lot. I see two ends here on Zoom. So the first one was Valentina Todorico.
So I have a question on this plot that you're showing here. So there is kind of a bimodal distribution of the metallicity with a peak close to solar, let's say, metallicity. Why is it so? Also in the CGM, for example, I don't expect such high metallicity at this redshift, for example. Yeah,
so this is probably, it's just due to the broad cut that we're making, right? Because I'm looking at the CGM across all of the box, and we're not looking at, I didn't look at halos in particular. I didn't go to a halo and decouple the ISM. I'm using some broad-based cut from a paper that says this is approximately where the CGM is. So the peak you're seeing at high metallicity is actually the ISM, or gas being ejected by stellar winds into what would be the circumgalactic medium. And the lower peak is inflowing gas that hasn't been enriched yet.
Okay. Thanks.
Yeah.
Thank you. So I would say Romil, please.
Hi, Doug.
Hello.
So I was wondering, this plot again. So it looks like the overall metal content is higher once you include mixing. Is that right? Because it seems to be above everywhere, and I'm wondering why that is. Is there more stars formed, or?
It's because you can't see the last bin.
Oh, okay.
Where the height changes.
Right,
So there's actually much more unenriched gas. There's much more unenriched gas with no metal mixing.
I see. Okay. So
yeah.
It's just an issue of the PDF. So is there any difference in the amount of stars that actually form due to the difference in the metals?
There's no significant difference in the amount of stars that form. It seems to mostly impact the metal distributions themselves.
Right.
Okay, so it's now break time, so we have a 15 minutes break. Of course, everyone is very welcome to stay and keep discussing, provided that Doug and the other speakers are willing to do so, because there are still a few questions. So yeah, if anyone, so the talks will restart in 15 minutes. But yeah, I would say just let's use this Zoom as a coffee break session, and we can keep discussing. So I don't actually remember the third end that was on Zoom, but yeah. Vadim, yeah, please.
Hi, yeah, that's a great talk. So I had a question about the results on converter in this idealized turbulent box tests, and it showed that there are different like Smogrinsky model, which is like relatively simple, and gradient models, which are a bit more complex, they produce similar results. So I was wondering if it's possible to look at some high order statistics, like some correlations between metals and velocities or densities of gas to distinguish between the models. Or did you try it?
I didn't try it because luckily, well, I mean, I would have done it, but luckily there was a paper that came out while I was working on this where they did post-processing on turbulence boxes and looked at some of this stuff. Like they looked at, kind of like what I did with the metals, where I degraded the resolution and then they compared the prediction from like a very, very high resolution simulation on large scales. And they looked at everything, especially with the gradient model. This is Hu and Chang 2020. They looked at these things which you're asking about, and they showed that the gradient model actually did predict everything much better than the Smugrinsky model when you were looking at these quantities. However, if you're more interested in something more broad brush, it doesn't seem to matter that much. But for sure, it does make an improvement in the quantities you're interested in. Mm-hmm.
I see. Okay. Yeah, that's very interesting. Thank you. Huge fan.
Mm-hmm.
So I see on Slack there is a question from Christian, but I don't see him here. So maybe he's gone for a coffee. I will just take advantage and ask you a question. Then I let you go for the break, I promise. So you said that, yeah, simulation like Illustris and Simula don't have this. So the obvious question is, why? Do you know why? I mean, if you said it can be calibrated.
Well, I think they think, well, at the time, maybe it wasn't clear that it could be calibrated. I think I read that in the original Eagle paper. It was unclear what kind of calibration you should have. In our 2019 paper, we showed that you can actually predict what the coefficient should be at simulation time, although it's very expensive. In our latest paper, we showed that it actually doesn't matter that much because you get the same result either way, even if you get something that predicts the calibration at simulation time. But it's not just Eagle and Illustris, and it's not like their fault or something. It's just there's any simulation basically doesn't include this. I think Semenov has worked on this a bunch, Vadim, and Wolfram Schmidt has done a lot of work on this. But this is more on the grid side of things than the particle-based stuff, which I'm working on. The fire team includes it. Anyone who works with gasoline 2 probably uses it. Like the Romulus simulations, they include it. But almost everyone else doesn't. So hopefully we move towards using this, especially when it matters so much, the time scale, at least in the early universe.
The plots you showed were impressive. If we are trying to essentially understand metal distribution and production. Of course, simulation are one of the main tools, right? So it's not, for someone working with simulation like me, it's actually scary.
Yeah, I just wanted to add about why models like this are not used in simulations like Illustris or Eagle. One reason is because to properly model subgrid turbulence, then some fraction of the onset of the turbulent cascade must be resolved. And while it's might be okay in zoom-in simulations like fire, in Eagle or Illustris simulations for resolutions like kiloparsec, it's much harder. Speaking of the turbulence in the interstellar medium, maybe it's for like turbulence in the CGM or AGM, it's easier because the scales are much larger.
Yeah, I'll add to that too. I mean, it is very interesting, right? Because people, when you get down to a low resolution in a halo, people start quoting the big numbers rather than the cubed number. So they'll say there's like 100,000 particles in this halo, but really there's 64 cubed, and you can barely resolve turbulence at all on that. It's mostly just dissipation in these methods. There's no turbulent cascade at all. So something like the method I was talking about, where you can calibrate it at, or calculate the coefficient at simulation time, wouldn't even work because there is no cascade to even look at to see what the value should be. But there are projects like Flamingos, I think, is coming out, which is Eagle at a very high resolution in a large volume, and that might be approaching something more reasonable, especially for the CGM, for sure.
I didn't mention that, but of course, if any of the speaker of the next session want to try out the slides, you are most welcome to do so.
Hey Enrico, so let me
Hey.
try.
Yeah, please.
I can try if you just because you ask. Let
Yeah.
me check that and share the screen. So can you see the slides?
Yeah, the slides. Yeah,
Perfect.
seems to work.
Seems to work. Thanks. Thank you very much. I'm just going to stop sharing.
Yeah.
I'm the second speaker, so.
Yeah. I mean, it's to be on the safe side. Normally, after 2 years, I think everyone is kind of used to this, more or less, but you never know.
You never know what's going to happen.
Indeed. Oh, hey. Yeah, can see it.
All good.
I don't see it moving. I just see the. Okay, now yes. Okay.
Everything look good?
Yeah, it does. Sorry, I was muted. Yeah, it does.
Yeah, thanks, Mark. Start in 2 minutes. Okay, so we started the second session of today with Mark Rafalski that will talk about the metal enrichment of neutral H1 gas over cosmic time.
Oops, there we go. Thanks. Yeah, so thanks for having me today. I'm Mark Rafalski. I'm the COST branch lead at Space Telescope. And today I'm going to tell you about the metallicity evolution of neutral hydrogen gas over time. So throughout this conference, you've been hearing and you're going to hear about metallicity from emission line diagnostics. And those often depend on temperature, density, ionization, and so forth. And so this talk's a little bit different in that we're going to be considering gas and absorption around galaxies and within galaxies. And we're only going to consider neutral gas. And this allows us very robust metallicities where we measure the metal line, the column density of the metal lines directly, and the hydrogen gas directly. And the ratio of those two gives us a metallicity. Specifically, I'm going to focus on damped Lyman alpha systems, or DLAs. DLAs are atomic hydrogen gas layers measured in absorption to a background quasar with a minimum column density of 2 × 10⁻²⁻. And the hydrogen column density is easily measured from the damping wings of the DLA, as you can see with the red arrow. And this is in the forest, and then the metal lines are measured to the right, outside of the forest mostly. Some distinguishing characteristics of DLAs. First is the gas is neutral, and this yields robust metallicities. Second, the metallicity is very low, at a redshift of 5 on the order of 100th solar. Molecular fractions are also very low. So what exactly is the metallicity evolution doing? So this is a plot showing the metallicity versus redshift, where the gray and green points are individual metallicities in DLAs, and the blue points are the column density weighted mean metallicities. So this is equivalent to the cosmic metallicity. And we then have a linear fit to these data points, to the blue points. And there'll be 3 things you should notice on this plot. The first is there's a metallicity floor. That is to say, we're able to measure metallicities an order of magnitude lower than what we're showing here, but they typically don't exist. And there are a few measurements at below -3, so below 1,000 solar, and those are usually targeted versus these are selected to be as unbiased as possible. But typically we don't see very low metallicities, although 1,000 solar is pretty low. We see a large dispersion, and this is real. This is not uncertainties in the measurement. This is variations in the metallicity of the DLA systems. And this is likely due to the mass metallicity relation and the varying masses of the galaxies that the DLAs are probing. And then lastly, when you look at the green points, you'll see that as we go to the highest redshifts, it looks like the metallicity is decreasing faster than this linear trend. And so that's what we'll be talking about a lot today is this real? Here we show 16 measurements at redshifts greater than 4.7, and this is still in the small number regime. And we'd like to see if this trend continues. But before we do, if you take the column density weighted mean metallicity of those 16 systems, you do get this brown point, which is 6 sigma below the linear line from the blue points. So we want to understand, is this real or not? And given the audience today, one of the things many of you are thinking about is dust. And how does dust affect this metallicity evolution? And I want to say, dust is definitely a factor in DLAs, but it affects systems with higher metallicities more than systems with low metallicities. And so if anything, dust would make this even the real effect larger than what we see, because the systems at higher metallicities would be affected more by dust. And so their true metallicity would be higher, and the systems at lower metallicities are affected less by dust. And so they would be affected less. And so this sudden decrease in metallicity is not likely due to dust. So it's something else. And so we'd like to get some more data to try and understand this better. So we can go to the literature and say, what's happened since 2014? And we have a few things that have happened. We have twice the highest redshift system discovered. One was at redshift 5.9, the other at 6.4 now. And both of these are approximate DLAs. That just tells us they're within 5,000 kilometers per second of the quasar. Now, these systems are likely unassociated with the quasar itself, but they're close enough that their metallicities are possibly affected by the quasar itself. But they're very low metallicities, consistent with what we've seen at lower redshifts, and we got to be careful about using those. There is a system discovered in 2018 at redshift 4.8, and this is at a metallicity of -2, and that's totally consistent with the other measurements I've been showing. There are other sub-DLAs discussed in that paper as well. We're limiting ourselves really to an H1 column density of 20.3 log n. And then lastly, there's a 2020 paper reporting 4 new DLAs. And I just want to caution with how systems are selected. And so what I mean by this is, in general, we go to lower resolution, low signal and noise spectra of quasars to identify the quasar and often to identify an absorption system. But in the plots I showed you, we never select sources based on the existence of metal lines in the spectra, because if you do that, you're going to bias yourself to systems with higher metallicities. And so this was done in this paper, though, so we have to be a little careful about biases. But it's, again, small numbers anyway. One of those DLAs is actually potentially not a DLA. We excluded it in 2014 because we thought it was less than 20.3. They say it's exactly basically 20.3. There was one that had a previous metallicity measure that's already included in the grade points shown previously. Another is at low resolution. So because we want to avoid saturation effects, we have to limit ourselves to higher resolution data, typically greater than 8,000. Otherwise, a lot of lines are saturated and you can get the metallicities wrong. And then lastly, there's one new system at 4.6, which is a lower limit. We previously had a lower limit on the metallicity, or I guess it's currently a lower limit on metallicity. So to show this graphically, here are the new points, and it doesn't substantially change the picture at all. But it doesn't add a lot yet. So we need a larger sample that's selected in an unbiased way. And the way we do that is we go to WISE. So the Sloan spectra have been exhausted to find these high redshift quasars and the absorbers in those quasars. So we need a different method. And here there's a color selection technique to select very bright high redshift quasars. They followed up with low resolution spectra just to confirm that there's a quasar. And then we have these samples. And from these samples, we had 2 X-shooter programs to observe them. And again, these are only selected based on that there's a quasar that's bright enough to observe. We observed them with at the high redshift. A resolution of 8,000, good signal and noise greater than 10, good wavelength coverage. So we have 41 new redshift greater than 5 quasars, as shown in the histogram below. And then we combine this with another sample, which is from the 2014 paper and some data after that using ESI, which exhausted the remaining BOSS, Sloan DR9 and DR10 selected systems. And here, 20 of those were selected without any consideration of if there is an absorption line already in those spectra. So we include those, but they do overlap with the 2014 paper. But in total, we have 61 high resolution spectra. And if you look at the search path versus redshift below, this is comparable, a little higher than the previous survey looking for a lot of high redshift quasars called GGG, but that was much lower resolution. But we're similar size. So how many DLAs are in this sample? Well, if you look at the 20 ESI samples, there were 4. Now, these are typically slightly lower redshift than the higher X-shooter sample, where we had 5. And out of those 5, 1 is approximate, so we exclude it. And just to kind of give you an idea of our ability to find these systems, I show the hardest one, the highest redshift system. This means that the density of the Lyman alpha force is highest, as you can see to the left of the peak of the quasar. So we can still, at the resolution and signal noise we have, go out to redshift 5.3. And so this is just to show we're confident in finding our DLAs, and this is the hardest one. But one thing you'll note is we found a lot fewer DLAs than would have been predicted by previous surveys, like GGG. And just a very quick aside on this, because it is related to the metallicity. This shows the incidence versus redshift, and you can see it generally 2 minutes increases. I thought okay. Well, I'm going to go. So it's lower than expected. You can get the mass density. It's also lower than expected. This is really interesting, but we'll have to leave this for another time. So here is the metallicity evolution of with the new 4 data points. As you can see, they're consistent with being lower. And if we want to say, are these the same? You can look at the histograms of the metallicities, and the gray are the gray points, the green are the green points. Purple is as if you take the gray points, evolve them along the linear relation, because you want to compare like metallicities. You don't want to compare metallicities from 2 different redshift ranges, because we know that they would be different. And if you do this, you see that the Kolmogorov-Smirnov test says the null hypothesis, the distributions are the same, can be rejected at more than 3 sigma. And then you can take the column density weighted mean. It doesn't change much. We're still 6 sigma below the linear trend. But we can try and understand what's going on here. And there's 2 different manifestations that could be happening. One is that as you go to high redshift, the galaxies that host DLAs are neutral out to larger radii. And so when you have a random sightline that goes through, you could have a lower metallicity because you're at a larger impact parameter and therefore at a lower metallicity due to the metallicity gradients. Alternatively, but similar, simulations show that the neutral fraction increases as you go to higher redshifts. And so therefore, all of a sudden, filaments and cold flows could cause DLAs, while at lower redshifts, this is not typically the case. So those are, of course, more pristine gas and lower metallicities. Together, you would still expect to see some higher metallicity DLAs at high redshift, but you just expect to see more lower metallicity systems like we're seeing. Another alternative would be that there could be a change in the enrichment mechanism of how the DLAs are enriched. So specifically, is there enough time for type 2 supernova to go off? Or is some of the enrichment that we're seeing due to earlier parent stability supernova from POP3 stars or something else? And you could look at the ratios of metal lines, as some people are doing, like Cookie and Welsh, and I won't get into it today because of time. So I'll leave up my summary slide just to say that we looked at the metallicity evolution of DLAs. We still see a more rapid decline at redshift greater than 4.7. I just discussed a couple of reasons why that could be. We also see a change in the incidence of DLAs and the mass density of DLAs at a similar redshift. They might be related, but we are in still the small number statistics regime. So we would like more data to confirm that we are really seeing what we think, which is that there is a change in how the metallicity evolution of DLAs is occurring. Thank you.
Thank you very much, Mark, for the very interesting talk. So for the moment, I don't see a question on Slack or on the. So I have several questions for you, but maybe I will start with one. So first of all, I wanted to ask you, how are you identifying, in fact, this high redshift DLA? Since already, I would say that at the redshift 5, it starts to be a bit complicated to select them from the H1 absorption, let's say.
Right. So that's a really good question. Because we're at a high enough resolution, a high enough signal to noise, we still can detect the DLAs from H1. So that's why I showed you the hardest one, the worst one at the highest redshift. And when you go to lower redshifts, it gets easier. So we are still finding the systems just fine. And we purposefully don't select the metal line, select based on metal lines to observe them, but we do see metal lines, right? So if we saw a system with metal lines, we could go and see is H1 there. Right. Given that in general, we don't see DLAs at below 10,000 solar, we should see the systems just fine. Thanks.
So another question from Annalisa, very rapidly, Annalisa. Then maybe you can go on talking on Slack.
Well, thanks. Well, thanks, Mark. It's really exciting to see that you are collecting all these super valuable data. One general comment, like you mentioned, dust depletion, the fact that metals are depleted into dust. Like you said that maybe for the drop, well, just a general thing, if you do take dust depletion into account, like the overall curve is much higher, because there's, I showed in the 2018 paper, there's 3 times more metals than what you're measuring there. So I encourage you to take the dust corrections into account. And then I have a question regarding the drop, because you mentioned that the work of Poodle, they were consistent with a drop, but in fact, I think their work, they just meant they came out saying that it was not consistent with having a drop. So I'm confused here. Can you comment on that?
Yeah, so let me answer your first question. So I'll answer both questions. So the first question is dust. And I agree with you totally. We should do dust corrections. And I was actually waiting with publishing this work because I want to include dust. The problem is we don't really understand how the dust behaves at 1,000th solar, even at 100th solar. And so the way to do this is, of course, to go and look at stars and try and at very low metallicity. And I'm working with Julia Ramon Duval to try and do just that, to get a better understanding of what is the dust doing so that we can correct our measurements for dust correctly. And I totally agree with you that it'll affect things. We do try and use transitions that are less affected by dust, but there is always dust. And that's why I talked about the relative change, how dust would accentuate that change rather than remove it. So the second question is, I'm sorry if I said that Poodle, I said their measurement is consistent with the drop, and not that they say that there's a drop. They definitely do say that they don't see a drop, but I was trying to show that they're being very cherry picking in their data. And then they're using samples that are selected in a biased way. And so the end result is, if you preferentially select some systems and then you add in new systems, including sub-DLAs, which aren't 100% neutral, and don't include ionization corrections, and coming from, so you're adding a new sample, which it's not a good sample, and then you cherry pick your sample of what's already there, you're going to get an answer. And in that answer, they don't see a drop, but I'm skeptical of that result. And I'd like, yeah, the fact when I go out and get more data, it's consistent with what I saw before, to me suggests that a more careful analysis was warranted.
Thank you very much.
I'm sorry, I can't hear you.
Can you please stop sharing? Sorry, I was muted. Okay, thanks. So we go on with Daniel Severino. That will talk about weak evolution of the mass metallicity relation at cosmic dawn in the first light simulations.
Thank you. Can you see the slides?
Yes.
Good. So hi everyone. I'm going to talk about the mass metallicity relation in the first light simulations. This work was mostly done by Ivana Langan, who at that time was a master student at the Cosmic Dawn Center in Copenhagen, and she's now doing her PhD at ESO. Also, this was done in collaboration with Christian Philanthrope, who is in the audience. So the main goals of this project is that we are trying to understand the metal content of these first galaxies at cosmic dawn, so somehow redshift above 5. And let us see the evolution of the mass metallicity relation, or just to see the emergence of this relation at high redshifts. If we can go from this scenario in which we see some pristine galaxies at high redshift, can we see the transition to the normal Eisen condition we see in local galaxies? And at the same time, we have to get some estimate of the gas metallicities and some metallicity indicators that can be used at these early times. So this is the main goal from the simulations. So this first light simulations is a large sample of galaxies in it's a complete mass selected samples, which means that within a given cosmological volume, we are selecting all the galaxies within a given mass range, with a halo mass between a few times 10 to the 9, now up to 10 to the 12 solar masses, at redshift 5. So we have a homogeneous sample of zooming simulations done with very good resolution, with a spatial resolution of better than 10 parsecs. So this is the largest database of zooming simulation with this kind of resolution, homogeneous sample of galaxies. The simulations are done with the ART code that includes a model for gas cooling, star formation, and feedback. You can see those papers if you need more details. So let me just give you some first results. We overall found a good agreement with observations. On the left, we see the UV luminosity function. On the right is the stellar mass versus the star formation rate. Sorry, each point here is a galaxy in the simulations, and we are in agreement with observation. These are the results from Salmon et al. Now we have extended that relation to much higher masses, to 10 to the 10 solar masses, a high redshift, redshift 6 or so. And also the unique property of these simulations is that we are getting good correspondence between the virial mass, the stellar mass, and the star formation rate of these galaxies. So this result here, we're in agreement with the estimation of this relation from Stefano et al. And also in agreement with other models like abundance matching high redshifts. So each point here is one of the galaxies in the first slide. So now we can study we can see the effect of this scatter, this relation on the net results. So for that, we are making mock galaxy catalogs for these simulations. This is one example of a mock SED of one galaxy, showing the stellar continuum. And on top of that, we have these emission lines. In particular, we're going to talk today of the oxygen 3 in the optical, which could be a good indicator for metallicity of this high redshift. We could expect that this line is going to be very strong in the reference optical. But at the same time, we can get the magnitude in the UV. So this is the stellar mass versus the UV magnitude. Now the points are color-coded by the specific star formation rate. So you can see we can extend the observation to much fainter galaxies, a redshift 6. But at the same time, you see some trend. You see that the galaxies at this have one dex range in stellar masses for a fixed UV luminosity. For example, if we now focus on a given fixed UV luminosity, we see large diversity of SEDs. One example, for example, this galaxy will have a SED with a very strong Barmel break and relatively lower line luminosities. This one will be like in the very high, with very low specific star formation rate. Another example with very high specific star formation rate will be this case. In this example, we don't see a Barmel break, but very high equivalent width of these optical lines. So this is the diversity that we can now see in the first slide. So this is just some examples of galaxies with the same UV luminosity, but very different specific star formation rates. So this first example, this galaxy is undergoing a burst of star formation with very high specific star formation rate. You can see that the gas is distributed on these giant clamps that contain most of the star-forming material in this galaxy. If we see a more typical example of a galaxy living on the main sequence, it will be here in the middle. Now the gas distribution, you see that the clamps are much smaller and they are extended. So they're distributed along the whole galaxy. On the other side, the galaxy well below the main sequence, now the gas distribution is very smooth with no clamps, and we see a very massive bulge at the center. So this is the diversity on the first slide that has some implication from the mass metallicity relation. So finally, this is the mass metallicity relation from different redshifts, from redshift 8 to redshift 5. So we see the relation at all redshifts. So we are only plotting here because we have large statistics. The points are color, so this is metallicity versus stellar mass. So the points are color-coded by the gas fraction. So we see some hints of the fundamental mass metallicity relation in the sense that now the yellow points are galaxies with high gas fraction that preferentially having lower metallicities for a fixed stellar mass. So we are resolving the mass metallicity relation in these galaxies, driven by this third component, this third property. But now we're focusing on the average property on these fitting lines. We see very weak evolution from redshift 8 to redshift 5. The relation seems very similar. If we look more carefully, we fix the stellar mass around 10 to the 8 solar masses. This is what we see. So this is the oxygen abundance as a function of redshift for galaxies with the same stellar mass, 10 to the 8 solar masses. So you can focus on the points with the error bars. So the error bars are just a description of the scatter of that relation. We see a weak evolution, but now the evolution is going in the opposite direction to what we naively think. So it means that the galaxies seem that are getting more metal rich as we go to higher redshifts. So we see, because we have very high statistics, this is a significant trend. How can we understand this trend? Because this is what the opposite of what we expect at lower redshift. So lower redshift, these are some observations. We go from redshift 0 to redshift 2. We see a decrease of the metallicity at a fixed stellar mass, consistent with on other simulations, that are the lines. So what we see in the first slide is a flattening of that relation. In something we see the inversion of the trend. It's redshift between redshift 5 and redshift 8. So how can we understand this inversion of the trend? First, we assume a very simple model. So in this case, we assume a pseudo closed box model in the sense that we have a constant effective mass metal yield. So in this sense, the metallicity only depends on the gas fraction. And that's enough to explain this weak trend. These are now the triangles, the red triangles. So that means that the galaxies with the same stellar mass at higher redshift have slightly lower gas fractions. That's enough to explain this trend. Because here we are not plotting the same galaxies, we are plotting a different population of galaxies all having the same stellar mass, but at different redshifts. So for example, we focus now on two populations, galaxy at redshift 6 and then blue galaxy at redshift 8. They all have the same stellar mass, but at different redshifts. We follow the evolutionary tracks of these galaxies. For example, this will be the blue galaxies. This is now the same metallicity versus a redshift, but now we have followed the same galaxies over time. As the galaxies are growing, the metallicity is increasing, as we should expect from these kind of models, because the stellar mass is also increasing. But now focus on the gas fraction. So the gas fraction of these galaxies, redshift 8, is slightly lower than the galaxies at redshift 6, which have the same stellar mass. So that's enough to drive this trend with redshift.
Minutes.
Okay, thanks. So finally, we are using some metallicity indicators. We are comparing this oxygen 3 H beta line ratio, the R3 line, as a function of the metallicity in the simulation or as a function of the stellar mass on the right. So first on the left, we see that some trend within the metallicity. This is what we expect for very low metallicity, because if we go to higher metallicities, for example, S2 region at redshift 0, we expect this to see this kind of branch. But if we are going to higher redshift, we have galaxies with much lower metallicity, we start to see the other branch in which the metallicity, the ratio decreases with decreasing metallicity. But also notice that the points are called the specific star formation rate. So if we have a galaxy or galaxy population that is somehow biased to our very high specific star formation rate, these yellow points, they can bias this relation because most of these galaxies are well above the average we found. On the right, we see the relation with the stellar mass. We see very nice relation between the oxygen 3 ratio and the stellar mass, with a threshold, with a cut or the strong decrease at very low stellar masses that could be barely seen with GWST. So yes, we go to the final conclusions. So all this data is available online. You can go to this website. So this is my summary. So the first light simulations follow the formation of the first galaxies. We found very little evolution of the mass-metallicity relation during cosmic dawn, mostly driven by the gas fraction. The oxygen 3 H-beta line ratio is a promising metallicity indicator, but still require some calibration, especially at high redshift and low metallicities. This is crucial, low metallicities. We also find variation in ionization parameter within these H2 regions that can generate variation or a bias on this kind of distribution of line ratios, even at the galaxy with the same specific star formation rate. So that's all. Thank you.
Thank you very much, Daniel. So questions for Daniel? So for the moment, I don't see questions. Yes, so there is one question from Yuichi Arikane. Thanks for the very interesting talk. Regarding the reason for the higher metallicity in higher redshift, why higher redshift galaxies have lower gas mass compared to lower galaxies at the fixed stellar mass, lower redshift maybe?
Yes, that thing I was going too fast, so let me go back here. So these are the two different populations of galaxies. They all have the same stellar mass, but a different redshift. Low redshift, and this high redshift, redshift 8. So the galaxies higher redshift, we call them early formers. So they form stars very fast, so they consume the gas much faster than the second population of galaxies that consume stars in a slower rate, because they achieve the same stellar mass but much later times.
Okay, so thank you. So for the moment, there are no other questions on Slack, but you can see later. Or yeah, there is a question from Annalisa, but maybe it's better if you write it on Slack, Annalisa, please, so that we can go on.
Okay, thanks.
Thank you. Okay, so the next speaker is Isaac Noel, that will talk about investigating the high redshift mass metallicity relationship through cosmological simulation. So similar topic, let's say. Please.
Hello. Yeah, thank you, Dr. Severino, for presenting on the mass metallicity relationship through first light simulations. I'm going to be presenting for the Croc simulations, which are very similar. So yeah, I'm Isaac Noel, a student from New Trier High School, and I'm a research intern at the University of Chicago. And so here are our findings on the mass metallicity relationship at high redshift. So as we know, the metallicity of stars in a galaxy gives us key information about aspects of a galaxy, such as when the galaxy acquired its star-forming gas and the impacts of inflows and outflows on the mass and metals of the galaxy. A well-studied and well-observed property of galaxies at low redshift is the galaxy mass metallicity relation. And as seen in numerous observations and studies, galaxies display a tight correlation between galaxy mass and stellar metallicity, as well as galaxy mass and gas metallicity. However, while we see an abundance of evidence for the mass metallicity relationship at redshifts less than 3, limits in observation technology have led to a relative lack of evidence for redshifts for the relation at high redshifts. And uncovering the high redshift mass metallicity relationship will help us better understand the behavior of galaxies at cosmic noon. And so to work around our current lack of observational data, we turn to simulations to help study the high redshift mass metallicity relationship. And multiple simulation methods analyze the evolution of the mass metallicity relationship at high redshifts, including the previously presented first light simulations. And on the screen here, we have some from literature. And these are the first light simulations that we just saw, and the fire simulations. These both use the popular zoom simulation method, which analyze a small sample of galaxies in very high resolution. And while their self-consistent physical processes are simulated with more detail, they are limited to a small sample size of galaxies, so their simulations could fail to model large-scale emerging patterns. In our study, we utilized data from the cosmic reionization on computers, or CROC simulations, which are large-scale cosmological simulations that study millions of galaxy halos at high redshifts, with the focus on cosmic reionization. They account for a plethora of physical processes relevant to cosmic reionization, from gas dynamics to star formation. The CROC simulations have a spatial resolution of 100 parsecs and a mass resolution of 76 stellar mass. They use the adaptive mesh refinement and they have multiple boxes of different sizes. For our study, we are using medium boxes of size 40 chimp, co-moving H-inverse megaparsecs. And each simulation includes a large number of particles. And for CROC, our study has a similar number of particles to the illustrious simulations. And we also include a variation of the medium box, which is overdense by 3 sigma above typical halo density levels. And we study this to probe the effect of the environment on the MCR, mass metallicity relationship. And from CROC, we use 6 different boxes, each one including data at redshifts 5 through 10. We used around 1E5 halos from each simulation, with each halo being comprised of a multitude of star particles. We then used the YT package to analyze star particles within the halos so that we could determine more details. And to avoid errors that arise when the size of our halos approach our resolution, we ignored halos with a stellar mass less than 1E5 solar masses. So we analyzed the star particles of each halo to determine the gas phase metallicities. And to avoid outliers, we found Z gas for each halo within the radius that contained 90% of the halo star particles by mass. This is the R90. We then loaded a new sphere of star particles with the new R90 of the halo and summed the mass of the metals obtained from type 1a supernovas and type 2 supernovas over all stellar particles and divided by the total mass within the R90 to determine the gas phase metallicity. And here are our results. So displayed are our results of the simulated mass metallicity relationship. The colored lines represent the relation at high redshifts, and the shaded regions represent the 75th to 25th percentile of the distribution. Across the halos in the CROC simulation, we see that the halos display a clear mass metallicity relationship, which flattens with higher mass. And this change in slope contrasts findings from some other simulations, including the first slide, that predict a linear mass metallicity at high redshift. We see a strong redshift dependence, which agrees with current theoretical models of galaxy formation, as according to the bottom-up hierarchical theory, low redshift galaxies are comprised of many merged high redshift galaxies. And so low redshift halos have matter that has gone through multiple rounds of star formation, and therefore more of its gas has been enriched with metals. As for the observed mass metallicity relationship flattening, we predict that this is due to galactic mergers, as more massive galaxies are more likely to gravitationally attract and merge with other galaxies. And it is found in CROC, star formation is less active in massive galaxies, which could explain why the mass metallicity relationship slows its rise. And then we continued our study by analyzing the stellar phase mass metallicity relationship. And to calculate the stellar metallicity, we found a mass-weighted average of the stellar particles. And as expected, this is very similar to the gas phase metallicity. The main observed difference is that the gas phase mass metallicity relationship is slightly higher than the relationship for stellar mass. And this difference agrees with current theory, as stellar metallicities reflect the gas phase metallicity when the star formed. So the stellar metallicities are the gas phase metallicities of the past, which experienced less rounds of metal enriching star formation. And combining this with the fact that star formation enriches the gas with metals as time progresses, we expect the stellar metallicity to be lower than the gas metallicity. And we now analyze the ratio between stellar metallicity and gas metallicity as halos age. Displayed is our plot of the metallicity ratio versus the normalized stellar age of the halo, which is calculated to be the age of the halo divided by the age of the universe at that redshift. And we normalize the age to remove any redshift dependence that's inherent in the age of the universe. So like the similar graphs, colored lines represent the relationship at different redshifts, and the shaded regions represent the 25th, 75th percentile of the halos. And there are singular points, which are just outliers, so it wouldn't have a very skewed relationship. And as shown in the figure, the ratio decreases with normalized halo age, which was found by doing, in that the normalized halo age was found by doing a mass-weighted average of stellar particle age. And so as we can see, there's no redshift dependence in this relationship, meaning that our halo samples have similar star formation histories. And because Z star is essentially a snapshot of past Z gas, the negative slope tells us that as halos age, the metal production rate is higher than the rate at which stars accrete nonmetallic matter. So that gives us some information about star formation histories. And here, these are our results from studying the overdense box. So radiation emitted by a galaxy may affect other galaxies many megaparsecs away. The radiative feedback is global, and since CROC simulates cosmic reionization, it's useful to explore the effect of the global radiative feedback on the mass-metallicity relationship. To observe how the galaxy environment affects the mass-metallicity relationship, we study halos from an overdense realization of our simulation, which we mentioned previously. And the plot displays our results. Here, the dashed lines represent the stellar phase mass-metallicity relationship that we discussed earlier, while the solid lines represent the mass-metallicity relationship in the overdense box. And here, they're displayed on the same plot for easy comparison. It'd be kind of difficult to tell if they were side by side. Our findings indicate that the mass-metallicity relationship in the overdense boxes is nearly identical to the mass-metallicity relationship observed in more realistic simulations. And we see the same redshift dependence as well as the same flattening. So based on our results, we expect that the mass-metallicity relationship is not significantly impacted by the large-scale galactic environment. And here's a comparison to literature and the first light simulations. So as observed earlier, many current predictions from simulations yield a linear high redshift MZR, but contrary to them, we see a mass-metallicity relationship that levels off with high mass. And our findings also display a stronger redshift dependence than previously found in the literature. And here we compare our findings to observation. So we tested our model by comparing it to the mass-metallicity relationship of nearby halos. Our predictions are reasonable when considering the observed mass-metallicity relationship at low redshifts. While some halos have a low metallicity, the overall shape of the low redshift mass-metallicity relationship lies above the high redshift mass-metallicity relationship with an expected distance. And this suggests that
2 minutes.
Okay. And this suggests that the redshift dependence will continue into the future, or into the present. And we also see that the low redshift mass-metallicity relationship takes a similar shape with some flattening going on at higher masses. And due to the limits in resolution that we mentioned earlier, we don't go before 1 E5 solar masses. Also, a recent development in the literature, a paper from Naidu has found that disrupted dwarfs whose debris constitute the stellar halo have lower metallicities by roughly 0.3 to 0.4 dex than the Milky Way satellite galaxies. So these findings suggest that the observed local low mass galaxies might actually have lower metallicities than what's plotted in the figure. And that's interesting to note. And going forward, so now that JWST has successfully established itself, yeah, there's a question.
And maybe you can finish.
You can
I think.
finish.
Yeah.
Yeah, you can finish.
Okay,
Please.
okay. Now that JWST has successfully established itself at L2, we can expect larger samples of fainter galaxies, and spectra from high redshift galaxies will prove to be a particularly important tool in analyzing the high redshift mass-metallicity relationship outside of theory. And I think at this conference, we have some findings from high redshift galaxies, I think from Yuichi. So these observations will open the door to theories surrounding galaxy formation and evolution in the epoch of reionization. From new empirical data, we can also learn about how we predict the mass-metallicity relationship. In addition, there are predictions for the high redshift mass-metallicity relationship from modern simulations. And each simulation uses different methods and prioritizes different physical processes. And confirming or denying any simulation's prediction will not only give us insight into the state of the universe at cosmic dawn, but it would also give us information that would lead to changes in our simulation methods. Perhaps we will see another mass-metallicity relationship entirely, indicating that there is an aspect of high-redshift galaxies that we've yet to consider. There's much to discover about the universe, especially with the trove of JWST's new data. That is all.
Okay, thank you, Isaac. So, Daniel, maybe you had a question?
Yes.
We have.
Was basically a very specific question about your definition of gas metallicity. So maybe because before doing any kind of comparison among different simulations, we should agree on the definition, right? How do you define the gas metallicity?
So we found like the mass of the metals emitted by supernovas over the total mass of the gas. Or yeah.
So this is weighted by the whole halo.
We found that within the sphere. Yes, I believe the halo.
So it's the gas metallicity in the halo, within the halo, within the whole galactic halo. Okay.
Yes.
Okay, at least in the first light simulation, we define the metallicity of the star-forming regions within the galaxy, taking into account only the stars, I think, younger than 10 million years.
I will double check.
So that's so maybe we are talking about different definition of metallicities.
It's not within the whole case.
Oh, it is
R90.
stellar particles. It is. I was incorrect. It was yeah.
So it's taking all the mass in metals within the galaxy, right? It's not the amount of metals in the star-forming regions, or the metallicity in the star-forming regions.
It's within the R90. So we summed the massive metals from the supernovas and over all the stellar particles, and then divided by the total mass of the R90.
The total mass of gas within R90, right?
Yeah.
Okay, so in that case will be the galaxy average metallicity.
Oh,
yes.
Okay.
Thanks.
Okay, thank you. So have a look also at the Slack channel, because there is another question from Christian Fillator that you can answer later. And now we can, with the next speaker that should have been Tanita Ramburut-Hart, which however today has a problem with her voice. So Annalisa very kindly is giving the talk for her.
Yeah, thank you very much, Valentina. Let me share again my screen. Do you see it's in full screen?
Yeah, yes, please.
Fantastic. So indeed, I'm gonna give this talk on behalf of Tanita, who very unfortunately lost her voice today. So she's actually present. She's a PhD student working with me, and please do write her directly on the Slack. Also for questions, she will be very happy to answer you directly. So I will discuss today the project that she is working on and she's hoping to submit soon. So it's about chemical inhomogeneities in distant galaxies. So the metal and dust enrichment and variations within absorbing galaxies between redshift 1.7 and 4. So I'm really happy that Mark gave some introduction about galaxies in absorption. So we are studying galaxies through their gas content. And this is useful because gas is a very fundamental ingredient of galaxies. Of course, you've seen these pictures. We're going to have, we have accreting gas on galaxies and outflows. And these are really fundamental parts and fundamental ingredients of galaxies. And one very good way to study the metals in this galaxy ecosystem that takes the gas into account is studying them in absorption. So we are studying damped Lyman alpha absorbing systems, so DLAs, and these are systems that have a very high column density of hydrogen, so that they are really associated with gas inside and around galaxies. So it will be the green patch here in this simulation. So they're kind of the densest regions. So by studying galaxy in absorptions, we also can see the smallest and faintest galaxies at high Z, which is the ones that are typically missed in normal surveys in emission. So in this project, what Tanita does is looking at DLAs, but not one whole DLA as a whole, but she looks at the components, the individual components along the line of sight. So we look at line profiles, and they have like different velocity components, like you can see these ones in different colors, and they are associated with different clouds along the line of sight inside the DLA system. So for once, we are asking, what is the chemical enrichment in these different clouds? So inside a DLA system. So with high resolution spectroscopy, one can study the individual gas components. And of course, we cannot then get the metallicity of these individual components because we don't have the hydrogen for the individual components. We can only look at the metals. But then we can look at their chemical enrichment by studying the dust depletion. So in this work, the chemical enrichment and variation was assessed or studied for a sample of 74 DLAs in that redshift range. Our word on dust depletion, this is the phenomenon that takes away metals from the gas phase. So the metals are locked into dust grains and they're no longer observable in the gas. So we go from elements that are less refractory, so they are less readily into dust grains, and elements that are, refractory elements, they are easily depleted into dust, they form dust grains, and the volatile elements instead, they are more, they don't form dust grains so easily. So we know how much each element should be refractory. And so we look at the depletion patterns. So we take the observation of their column densities. And here we look at the equivalent metal column, which is basically a measurement of their column density, but weighted by their solar abundance. So if there is no dust, these measurements, they could line up on a horizontal line. So the slope of the fit through the measurements tells us how much dust there is. If this slope of the depletion pattern is flat, it means no dust. If it is instead very or steep, then it indicates that there is more dust because indeed the refractory elements like titanium and chromium deplete more than the volatiles. So the slope of this curve is what we call the zinc over iron fit, which tells us how much depletion we have. So really it is similar to a zinc over iron observed, but it's calculated by looking at all the metals globally and without measurement of the hydrogen. So this is a measurement, we can use this measurement of the zinc over iron fit of the depletion as a proxy for the metal enrichment overall, because we know that there is an overall relation between how much dust we have, how much depletion, and the metallicity overall. So Tanita looked at very many, these 74 DLAs and looked at the different individual components. And this is one example of a DLA towards this system at redshift 2. And here she shows a few of its components. It actually has 19 components. And then we are looking here in each panel is a depletion pattern. So on the left side, you have the more refractory elements. On the right side, the more volatile ones. And then, you see these depletion patterns. So whenever you see a curve, like a linear curve that is rather flat, this means not so much dust. So this system here has a mild, like a low amount of dust depletion. While other systems, they have a higher amount of dust, and other systems like component 3, for example, has even a higher, or component 7. They even have a steeper slope that means higher amount of dust, so higher chemical enrichment in a way. And this is another example here that I will come back to later. So overall, this is what she found. Here you can see the depletion factors, or this zinc over iron fit, or how steep are these curves for the individual components. Here you have individual systems, And you can see that for some systems, you really see a high diversity. Not for all of them, but for some, you can really see a high diversity of chemical enrichment or dust depletion within one system. And here, there are the same measurements of zinc over iron fit, but now plotted against the redshift. And what I wanted to highlight here was the fact that these systems that have very low dust depletion, so low chemical enrichments, they are observed at every redshift, basically. And these, we think, are evidence for infalling gas that is more pristine, more like less chemically rich. So we can see evidence for this at any redshift. And then there is a second result that she got, and this was looking at the nucleosynthesis effects. So for now, I told you about dust depletion that shows up by making these depletion patterns more or less steep. But in fact, we could see deviations from these patterns. Like it's a higher level of complexity, and you can see like deviations from these patterns due to nucleosynthesis effects. For example, we know that core-collapse supernovae are the most responsible for producing the alpha elements, and on the other hand, the 1A supernovae are most responsible for the production of the iron group metals, including manganese. So what Anita found was that very often there was a systematic deviation from the depletion patterns that we saw. We saw very often like silicon and magnesium overabundances and manganese underabundances. So this was really observed in several systems. And here you have some examples from, for example, here you can see silicon and magnesium deviate by being above the linear curve and manganese below. Here again, silicon and magnesium above, manganese below. And so now here you can see the overall observations. So these are all the deviations that she observed. So the deviations from this straight line fit, which is somehow comparable to an X over iron, so to a relative abundance with respect to iron, but for after taking dust depletion into account. So this you can kind of compare a little bit more with stellar abundances. And so here you can see, this is on the x-axis, you have how much depleted the system is, so the chemical enrichment, which somehow you can translate into a metallicity. And you can see that she observed several cases of silicon overabundances and manganese underabundances. These are the deviations from the linear fits that they describe the depletions. And the curves here represent the alpha element enhancement and manganese underabundance for the galaxy. So this takes me to the third result. So one interesting thing that we did was then comparing the chemical properties and the kinematic properties of the individual clouds. And we did this to see whether there could be hints for perhaps inflows or outflows, like infalling gas that is more metal poor or outflowing gas that is more metal rich. And this is one example where there is a hint for a potential gas outflow with many caveats.
Yes.
Thank you. So this is a potential case where maybe an outflow was observed. So it's a case, so here again, you see the depletion factor, so how much depleted, dust depleted the system is, so the chemical enrichment, if you want. And on the x-axis is the velocity from the systemic velocity of the system. And you can see that in this system, there's a fairly high chemical enrichment in terms of the depletion for very high absolute velocity. So this may be a system that shows gas outflows. But of course, disentangling the outflows just from the kinematics and chemistry is not a straightforward thing to do. So in summary, studying galaxies by studying their gas content in absorption is a powerful method for obtaining information on the chemical enrichment of galaxies. And then with high resolution spectroscopy, we can study DLAs component by component. So not the total, but component by component, like the individual clouds or clusters of clouds. So what we find is, first, we find that several DLAs in our sample are chemically inhomogeneous, so their chemical enrichment is diverse. Then we found that we observed dust-poor components at all redshift, hinting at infalling gas. And then we found that well, we present evidence for nucleosynthesis effects like alpha element enhancement and manganese underabundance in distant galaxies. And then in combining the kinematics and chemical enrichment of these galaxies, we can hint at outflowing chemical enriched gas. So thank you very much on behalf of Tanita. And Tanita asked me to please redirect the questions on Slack, which you can perhaps try to answer on the spot, or otherwise she will answer them later. So let's see how this goes.
Okay, thank you very much. Very interesting work. So yes, so please write your questions on Slack so that Tanita will be able to answer them. And so at this point, we move to the last speaker of today, which is Harley Katz, that will talk about emission line signature of the POP3, POP2 transition. Harley, we don't hear you.
Sorry, can you hear me now?
Yeah.
Good. So thank you very much for having me. I'm Harley. I'm currently a fellow at the University of Oxford, and I'll be talking about some of the newest results from one of our simulations, mainly focusing on the emission line signatures of the population 3 POP2 transition in the early universe. So I should start by saying very little is actually known about POP3 stars in general, or the population 3, population 2 transition. For example, things like what redshift did population 3 stars start forming? When did they stop forming? Things like what was their initial mass function? Did they form in isolation, binaries, clusters, etc.? We also don't know much about their evolution and their impact on their environment, such as their radiative or mechanical feedback, or in particular, their chemical enrichment. What abundance patterns should we look for after the first generation of population 3 stars? What are the distribution of these metals? Did they stay in the halos? Did they get all the way out into the intergalactic medium? Also things like what's their contribution to reionization? Now, I shouldn't say it's all pessimistic, because of course we do have some constraints. For example, galactic archaeology can tell us some things about the lowest mass POP3 stars that could form, because if they were too low mass, they might have survived until the present day. But in general, since we've never directly observed a population 3 star, there's kind of a lot of room in parameter space to explore. Now, there's tons of simulations in the literature that have tried to model these types of galaxies and this physics. People have looked at things like the IMF from first principles, metal enrichment, formation redshifts, contribution to reionization, all these questions I just talked about. For some of the things, there is some consensus. So for example, at least for the formation redshift, that more or less goes when we think overdensities can collapse, so maybe sometime between redshifts 30 or 40 or so. When they stopped forming, that's still under debate. And then things like the IMF in particular, there's not really a good consensus in the literature. This is just a table from some work by Athena Stacy. It's a little bit outdated now from 2016, but if you just look at the far right column and look at the median mass of the stars, you can see that there's a very big difference in what masses are being predicted for population 3 stars. Nevertheless, JWST is in the sky, which is super exciting. And I think this telescope in particular is hopefully going to provide us with better constraints on what the properties of POP3 stars are. So one of the things we need to know is what are the spectroscopic signatures of the population 3, population 2 transition, so that we can make the most sense about these observations. Now, there is indeed a rich literature on what we should look for when we're trying to find these pristine metal-free stars. Of course, the first thing that comes to mind is if you see the spectra of a galaxy and it has no metal lines, that's one indication that it might be a population 3 galaxy, although we'll return to this assumption in just a little bit. There's been tons of work, mainly using photoionization models such as Cloudy or others to try to predict these emission line signatures. An example here is shown on the left. Daniel Scherer showed very early on in 2002, 2003 that these galaxies are expected to have very strong hard emission lines. For example, the helium-2 1640 line. People have looked at what the galaxies will look like in JWST colors. And then more recently, there was a paper by Nakajima and Maiolino showing that perhaps going into the optical and looking at things like the equivalent width of the 4686 line against H beta might allow you to differentiate between population 3 stars and direct collapse black holes. However, all of these models are really quite idealized. They often assume a homogeneous medium, things like continuous star formation rates or single bursts, and it's not clear that they fully capture the physics of what might be going on with at high redshift. So I think it's an important exercise to test a lot of these diagnostics for population 3 stars with simulations. Now, I'm going to argue to you that the current state-of-the-art simulations aren't really fully up to the task for this. And ideally, a simulation would contain all of the necessary physics to self-consistently predict emission lines from both primordial species as well as metals. But that's generally not actually the case. In fact, the current way we usually do things is we run a very high resolution simulation, an example here from my 2019 paper shown on the left, where you try to semi-resolve the ISM as much as humanly possible. And then you have things like your gas distribution, molecular hydrogen, your temperature maps, metals, dust, stars. And if you've run the simulation with radiative transfer, you also have the RT field. And you plug all that information into a photoionization code called cloudy, or any photoionization code for that matter. And then if there's dust in the system or the line that you're looking at is resonant, you have to do additional post-processing steps such as dust RT or Monte Carlo radiation transfer. And then eventually, after a lot of CPU time and manpower, you can produce these beautiful emission maps, which I'm showing you here on the right for whatever emission line you're interested in. However, there's, of course, a number of assumptions that go into making these predictions, one of which is that the system is completely in equilibrium, which of course might not be the case. So we decided to go out and try to do this better by developing a brand new code. And this code is called Ramsey's RTZ. And the way you should think about it is it's essentially a 3D non-equilibrium version of cloudy, where what I've done is I've taken all of the different processes that are important for setting the ionization states of primordial elements and metals, and I've plugged them into the Ramsey's RT code so that we can predict both primordial, metal, and now even molecule ionization states on the fly in the simulation. So to show you what this looks like, here I'm just showing you a setup. It doesn't really matter what it is, but there's a bunch of different elements in this plot going from oxygen, nitrogen, carbon, and magnesium. Each of the different colors represents a different ionization state, and you just evolve this system. You can see that the ionization states are changing. Now, the dotted horizontal lines represent the equilibrium abundance, and this is the abundance that you'd predict from a code like Cloudy or really any other photoionization code for that matter. But of course, the true ionization states in a non-equilibrium sense could fall really anywhere along this line. And if your system happens to be out of equilibrium, you're going to get your emission lines wrong. One of the nice things about this code is we can solve the cooling now on an ion by ion basis by just solving for the level populations, which also gives us the emission lines directly on the fly in the simulation. So an example of what this looks like, this is just a really low resolution isolated galaxy where you can see that the top left image shows you the gas distribution. And if you just follow the left column down, you'll see both the neutral hydrogen and molecular gas. But the new thing with this Ramsey's RTZ code is that in addition to these primordial elements, you couple the radiation field to all the different metal species. So depending on the different ion you're looking at, for example, in the top row, oxygen 1, oxygen 2, or oxygen 3, you can see that the galaxy actually looks fundamentally different. And if you go one row down, you can see the same galaxy, which is edge on. And if you look more towards the outflow, you can see the different ionization states are changing as you move further and further away from the galaxy. So moving back to high redshift, what we wanted to do is apply this code to the population 3, population 2 transition. We're calling this simulation the high redshift Pathfinder simulation because right now it's only one, but ideally we'd have a few more with more additional CPU time. And it's really a high resolution simulation of an individual galaxy. It's got a dark matter particle mass of around 500 solar masses and subparsec resolution at redshift 10. And includes things like models for population 3 and population 2 stars with different IMFs, SEDs, et cetera. We follow the enrichment of a bunch of different elements, as well as the connection between the radiation transfer in 8 different bins from the infrared all the way up to the UV, completely coupled with the cooling and chemistry. Just to show you an example of what this looks like, on the right, you're seeing in the top row a map of the dark matter distribution, gas distribution, and the oxygen distribution. The circle is showing you the virial radius of the halo. And you can see that by redshift 10 or so, there's actually quite a bit of enrichment of oxygen moving out of the galaxy into the intergalactic medium, but it's still fairly patchy. If you go to the colorful image just under it, what you're looking at is the nebular region inside of the halo, where now we can directly predict from the simulation the distribution of different ionization states, for example, of oxygen. So you can see this beautiful nebula made up of oxygen 1 in white, oxygen 2 in pink, and oxygen 3 in yellow. So since we have models for population 3 and population 2 star formation, we can just look at things like how is the star formation rate dominated by each mode of star formation, each mode of stars as a function of time. So on the x-axis, you're looking at the time in megayears and the star formation rate on the y-axis. The cyan lines represent POP3 star formation, where the magenta lines represent POP2. And what you can see is that at early epochs above redshift 14 or so, the star formation rate of this galaxy is completely dominated by POP3 stars. But then once there's a little bit of metal enrichment, you move into a mixed phase between POP3 and POP2 stars. And then finally, by redshifts 10 or so, it's completely dominated by POP2 stars. Now, I should mention that this timing of the transition between POP3 and POP2 is completely dependent on the collapse time. So this result is not supposed to be a general thing. It's just what happened for this particular Lagrange region. Another nice thing you can look at is the metal enrichment of individual metals. You can look at that in a mass-weighted sense on the top or a volume-weighted sense on the bottom as a function of time. The POP3 stars, once again, form around redshift 16 or 17, and you can see that there's a big supernova feedback event, which is blowing out things like iron in magenta, iron and cyan, oxygen in black, carbon in magenta into the universe. It sort of plateaus at a metallicity of around 10 to the -4 solar until we reach around redshifts 10 or so, when we have this full POP2 transition where you see the metallicity really start to rise again. Different elements are going to be enriched depending on the different modes of enrichment, whether it's POP3 stars, POP2 stars, stellar winds, et cetera. So you can see that there's a late onset of nitrogen enrichment here. And of course, you can compare the mass-weighted sense versus the volume-weighted sense, where the volume is going to be much more impacted by inflows. So moving to the emission line signatures of these galaxies. 2 minutes. Moving to the emission line signatures of these galaxies, one of the things we wanted to do is check how easy it was for JWST to definitively find a metal-free halo. And what you can look at here is the metallicity on the x-axis versus the flux ratio of different emission lines on the y-axis. And if you just focus here on the left-hand plot, this is the oxygen 3, which is supposed to be one of the brightest emission lines versus H beta. And you can see as you go down in metallicity, this flux ratio significantly decreases. Compared to cloudy models, we're actually, it's a completely different technique for measuring emission lines, and it's great that they agree, but we do see some additional scatter, which is related to the star formation rate of the halo. But the point I want to make here is that there's actually some systems which are highly metal enriched that have very, very weak oxygen 3 lines. So if you go out with James Webb and you don't see metal lines, that just might mean that they're very weak rather than they're not there. So this is not conclusive for population 3 stars. You can move into a 2D diagram, oxygen 3 over H beta on the y-axis versus helium 2 over H alpha, which is essentially the hardness on the x-axis. And if you do this, you can find a little bit more differentiation. The pink arrows and the pink points of the galaxies, which are dominated by population 3 stars, whereas the cyan points are dominated by population 2. And in general, you see that the population 3 systems have hard spectra and weak metal lines, but indeed we actually do find some population 3 systems that do have metal lines, and this is results of echoes from things like supernova or pair instability supernova in this case. We also have a bunch of systems which scatter all the way down here on the bottom axis of this plot. All the way towards the right are star systems that have bright POP3 stars which are active, and the ones that are fading off to the left are the ones where the POP3 star has died. This is really important because it's not just the fact that a galaxy has a hard spectrum. You need to be able to catch the helium-2 emission. And an important consideration is that the helium-2 emission in 1640 fades off very, very, very quickly. So here you're looking at the time since the burst of population 3 stars versus the luminosity over the max luminosity of that system. And you can see in general for population 3 systems that the luminosity of the helium-2 line fades incredibly fast within a few mega years. This was indeed predicted by Daniel Scherer in 2002. We do have one system where it seems to extend to about 10 mega years, but this is actually the result of multiple POP3 stars forming at different times in the same system. So it's going to be very, very difficult to detect these helium-2 1640 lines. I'm actually going to skip this slide in the interest of time, but the point here is that you might be able to catch that fading distribution. However, as the helium-2 line fades faster than the Balmer lines, which means you're no longer in this hard region of the phase space. So to conclude, detecting POP3 stars or detecting the POP3, POP2 transition is going to be very difficult. POP3 galaxies, or sorry, population 2 galaxies might just have very weak metal lines below the sensitivity limit, thus might not be truly metal-free. The helium-2 signature fades very fast, so this might be problematic for the small field of view, but you might be able to detect some of this residual emission if you're lucky. So thank you.
Thank you very much, Harley. So, okay, first question by Daniel.
Hi. Thanks for the talk. It was really very interesting simulations. I have several questions, but I think the most important one is about the line luminosities. You are not using any subgrid model for metal emission, any clamping factor. In that sense, are the line luminosities that depends on the resolution of the simulations?
Yeah, I mean, in general, the line luminosities to some extent might be dependent on it, but keep in mind these simulations are like well sub-parsec resolution. So the resolution that we're running at goes all the way down to 0.4 parsecs in particular cases. So I think we're going to probably start to reach the point of convergence relatively soon in this. I mean, if you look at a typical cloudy simulation, it's not the individual zones are not much further resolved than that.
Mm-hmm. Yeah, but that could depends on the line of the ion that we are taking into account. If we are focus on the ion, for example, oxygen 3, that's really close to the stars, maybe you need even higher resolution.
Like, I'm not going to argue with you that higher resolution is always better. I think we can all agree that that's the case. That being said, I don't think we're going to get orders of magnitude more oxygen 3 luminosity. I mean, if you look at my plots compared to the results from cloudy models, they're in actually fairly good agreement. So considering that the individual zones in cloudy are in the order of well sub-parsec, it's not clear that adding higher resolution is going to change my results by more than by factors of a few maximum.
Okay, thank you. I don't know, maybe we can just answer to another question from Slack from Roberto Maiorino. Excellent work, Harley, as usual. Question, does the simulation include the contribution from X-ray binaries, which should be more important at low metallicities?
Yeah, that's a good question, Roberto. So someone perhaps that's more of an expert on this can correct me if I'm wrong, but the most recent version of the BPAS SEDs I thought did include some contribution from X-ray binaries, but I might be wrong there. As for the population 3 stars, we're assuming they're more or less forming in isolation. So if you have 2 POP3 stars that form an X-ray binary, we're not going to capture that fully in our simulation. But no, we don't do anything special other than use the most recent BPAS SEDs, at least for population 2 stars.
Okay, thank you very much. There are a lot of questions on Slack then that you can answer. So I would like to thank all the speakers of today, and so we meet again tomorrow at the same time. So I don't give you a time because that will be different from in every place. So yes, it would be 2 p.m. in UTC time. And so thanks again, and see you tomorrow. Bye bye.
Bye. See you tomorrow.